But hallelujah. Recording in progress. Great. So thank you for coming back for this second day episodes. Today we are going to do quite a number of practical exercises, trying different HPC techniques to solve some basic examples. Plus, we will use what we learned yesterday for executing our programs on Bura and seeing how different code, different implementations of the same task have different performance essentially, depending on what kind of tool we are using. So we are going to proceed like this. Most of the episodes today will be taught by me. With a brief break for GPU episode, which will be taught by me because, as we already mentioned, Bura currently doesn't have active GPU nodes. So I will show you, I will teach you a little bit about how we can use CUDA and higher level Torch library for executing code on GPUs, and I will demonstrate it on my laptop. So if you have an NVIDIA GPU card installed on your laptop, you can run these examples on your laptop as well. If not, you can try using Google Co-op. I will demonstrate you how to do this. Although in my case, not all exercises were able to run there because of the versions of the libraries. But still, it is a good option to try quickly some stuff. So we will implement this. As I already mentioned yesterday, please follow the code of conduct, be kind and inviting to each other, and if something is making you uncomfortable, please let us know. And that would be it from me. And Meet, I think you can start. I will allow you to share screen.
Thank you so much, Alex.
Go on. Yeah.
Yeah, hello everybody. Welcome to the second day of the InterPython workshop. Again, I would like to thank all of my colleagues who have helped for developing the lesson, as well as Tomislav and Gordon, who very kindly provided us access to Bura. What I would like everybody to do from the start is to try and log into Bura. So once you just open the web portal or just log into Bura, can you send me a thumbs up? Because today we are going to be doing hands-on exercises. So it is better to be logged into Bura, so we can actually run some stuff there, and we don't have to keep looking back and forth when we try to access Bura. Was everybody able to log in? Can you just either do a thumbs up or write in chat if you're able to log in? Just say yes. Alex, Marcus, and okay, Pals was available. Riley, Fatima. Okay. Uh, Navin and John are still left. Angelica is also done. All right. So, in the interest of time, let's start. So today we'll be learning about how we can actually use the different types of code architectures which are available on the HPC, and also look at how you can adapt your code, which is basically what you're running on your regular PC to work on a supercomputer, such as Bura. So before we get started, as I asked all of you to log into Bura, now you guys should follow these steps. If you didn't create a virtual environment yesterday, I would urge you guys to make a new virtual environment. For this, you would also have to load the Python module. So first load the Python module, and then you guys should be able to make a virtual environment, after which you can activate the virtual environment. And I would also urge you to load the other modules so that we can run all the programs that you're supposed to run today. Once you're done with that, can you just say yes in the chat? I'll wait for 2 or 3 more minutes.
Sorry, can we have the link of this page in the chat, if that is possible?
Yeah, sure.
Thank you.
Yeah, sure. Here you go. I pasted it.
Thank you so much.
If you guys are done, just type yes in the chat, Zoom chat, so I know that you guys are done, and then we can proceed forward with the. Great, I see a couple of yes already in the chat. Just waiting for everybody else to complete. Can wait for 2 more minutes.
So why do I get the command that like VAMP doesn't exist on my system?
Which one? Can you share your screen if you want? We can just solve it right now. Yeah, just go ahead, share your screen.
Yeah, sure. So I should be basically just doing this, right?
You should load the Python module first. So load, if you go back to that module, load Python first. No,
Maybe
module
this
load Python. Yeah, this one.
Okay.
Once you do that, you'll be able to yeah, and now just do Python mv enter Python. Yeah, and now source, the source one. You should be able to do the source one.
Okay, cool.
Yep,
Thank you.
go. You should also load the other 2 modules.
Sure.
Yeah. I think everybody else should be done by now. So let's start with the session for today. So first, let's look at how we can basically scale up our examples for using on HPC. So let's start from the basics. So we know that whatever our devices we use are pretty fast as compared to whatever we had in the earlier times. So like all personal computers can run basic code. We can do basic modeling of stuff, especially for astronomical applications. And we like have enough 16 gigabytes of RAM and like 4 to 8 CPU cores on our local machines, which help us in running basic tasks that we want to do such as like classification of like small things. And if you want to basically run some light curve plotting code and stuff like that, you can basically run it on your PC. But what happens if uh, when you actually run the code? When you run the code, the code, if you're just writing it in plain Python, what happens is you're only running it on one CPU with one core, which is not very efficient given that your CPU and your local machine itself has like 4 to 8 cores and 16 gigs of RAM, which you can be utilizing to its maximum. So in the first example, we will look at how we can make our code run faster on our local machine itself. So there are like two approaches. Either you can make the code run faster, which is what we're going to try to be doing in this session, or you can get better resources. You can get more RAM, get more CPU cores, which would in turn make your code running much faster. So let's say you are approaching a basic problem. So the basic problem is you have a big array of 100,000 numbers, and you want to add the numbers in the array. How would you do it? The most naive way to go about this is to use Python and just use a for loop. So if you have like 100,000 elements in your array, you're just picking one element, adding them, picking the sum, adding the next number, and then doing it 100,000 times. So I would like everybody to look at the serial code py file that they have. You can just do cat serialcode.py that you downloaded yesterday, and then you can look at this file. And as you can see, for writing serial code, which is just like adding one number after the other, which you're doing as a serial in a serial manner. You're taking one number, adding that to the next number, you are preserving the sum, and then you're adding the next number. You do it 100,000 times. This is not very efficient because you are just doing one operation 100,000 times. So how can we optimize that? One way to optimize that is by implementing the code in a lower level language. Now, what is a lower level language, right? So Python is basically a higher level language. Why? Because Python code doesn't directly compile to machine code. So like your computer works with bits. So it's like a pattern of zeros and ones that you pass on to the CPU or the GPU, and then you basically tell it what to do in your code, and then it gives you the output. But what happens is, in the case of Python, you need to have an interpreter, which basically takes the Python code, interprets it to machine readable code, which is basically binary zeros and ones, and then it passes on to the machine, which executes it and gives back you the output. Instead, in lower level languages like C, what happens is there is no intermediate step. The C code is a compiled language, which directly converts the code that you write in C to machine readable thing. So there is no overhead of interpreting the code to a machine readable language, which makes it more efficient. So if you're just using Python and you want to utilize functions that are available in C, such as vectorization, what is vectorization? Vectorization allows us to basically turn an array of like instead of just summing over an array of numbers one by one, you can just pick up the entire array and then sum it all together in one go using a function, which is what basically C does. That's why C code runs much faster than Python. And there is a way of basically using this C code in Python by using the NumPy library. So the NumPy library was introduced to make arrays and matrices in Python more efficient. So we can do that by using the numpy.sum code. So if you can see here, in the code that we are basically just trying to here we just add the number one by one, and then we record the start time and we record the end time, and we just loop over the entire array one by one, and we get the result. As you can see, the time taken for doing this is very long. It still takes a second, which in just adding a small array like 100,000 numbers is very large. Whereas if we use numpy.sum, which basically uh, converts the entire array to C-readable code, which is called vectorization. And because we use vectorization, we are able to like optimize the Python code in a much better fashion by using C under the hood with NumPy. And if you can see, if we do the same thing, we're just adding an array of 100 million random values, and we just record the start time and end time again. And if we just use np.sum instead of using a for loop, the time taken is way less as compared to the serial version. Then just using like adding one number to the sum every time. So we can also like reduce uh, our time just by optimizing our code by using libraries and functions which have specific advantages over the normal Python syntax. So this is the first step to optimizing your code. And if you just like if you're just like using Python's loops, these tasks, the loop overhead is actually a very big deal, which is basically converting the code from Python to machine language. And therefore, the first step to writing optimized code is by basically using libraries which allow you to do vectorization in Python. So does anybody have questions so far? Are there any questions for the same? All right. If not, can you guys see my screen? My screen suddenly disappeared.
Yes.
Yeah. Pardon me. Just a second. Yep. Okay. Yeah. All right then. Let's move on to the next one. Now, what we do is in some cases, what happens is we use vectorization for our last case, in which we use C code to basically C code under the hood to fasten our code in Python. But that's not always the case. Sometimes you cannot use, even vectorization does not help you to make your codes run faster. This usually happens when the code is memory heavy, as well as it requires a lot of calculations as well as logical processes. So let's say you are using a lot of if else statements, or you're using a lot of try else blocks, which basically make the CPU think. Like you need to have a logical process which is basically given to the CPU, and that you cannot vectorize as you cannot interpret it directly into C using Python libraries. So what do you do? So instead of like just trying vectorization, there's something called parallelization. So let's say you taking the light curve example again. What you have to do is that instead of now just adding an array of numbers, you are given to basically find the period of 100,000 light curves. How will you do it? There are again two ways to approach this. One, that either you basically just run each light curve one by one and then get the analysis of the period, or what you can do is you can basically create multiple copies of the same program and pass and divide it into chunks. And then instead of just using one CPU core and like one processor, you can actually use a lot of processors that are available in your laptop. So And especially in high performance computing systems, there are a lot more processors than what your uh, local machine has. So like if you're using a local machine, your CPU cores would be in the range of 4 to 8, maximum 16 or 32. But in high performance computers, the CPU cores usually are in the ranges of 128, 256, and sometimes even thousands, depending on the CPU in the HPC you have access to. So how do we make fully utilize the full utilization of these assets that we have in our hand when we get access to an HPC? What we can do is we can basically create copies of the same light curve. You can divide it into smaller chunks, and then you can pass it to different CPUs to run the same thing, because it's not that the period of one light curve is dependent on the period of the other light curve. These are independent events. When there are independent events which can be distributed into smaller chunks to run on separate CPU cores, that's when parallelization comes in. So like you can parallelize your code very efficiently just by taking code which can run taking code on events which can run independently and then dividing them into smaller chunks, and then giving them to different CPU cores to execute. So if you look at the example that we have shown here, so you're just trying to analyze light curves, which is nothing but when you're looking at an object in the sky and you're measuring how the magnitude or the brightness of the object changes with respect to time, and you're plotting it on a plot. So x-axis is the time plot, and your y-axis is how the magnitude changes with respect to time. One common goal of analyzing light curves is to basically look at the period of variability, like the light that is changing in the light curve varies in a period. So how do we do it? So to detect periodic signals in light curves, we usually use the Lomsky periodogram, and that in that way, like it just like plots the power versus frequency of the light curve, and then we can find the period of basically the whatever the how the brightness is changing. Um, that's not our main focus here. Our main focus here is to understand how it scales by either by using just one CPU core and one execution, and then instead of dividing the data set into separate smaller chunks and then passing them to different CPU cores and looking at how faster it works. So if you see in the plot, for a lower number of light curves, uh, the parallel versus serial execution time is almost the same. And then as you increase the number of light curves, the parallel execution takes significantly less time as compared to the serial one. The serial one uh, increases linearly, while the parallel one almost stays flat. This is because when you actually parallelize the code, you are actually splitting the data, right? You're splitting the light curves into smaller chunks. That takes some time. So instead of like just taking one light curve and analyzing it, second light curve and analyzing it for all the 100,000 light curves, you're basically dividing them in the first step, which is why you can see that for the initial like a smaller number of light curves like 10, 50, 100, 200, 500, the time is almost the same. But as the overhead of like the splitting is lessened by the number of light curves. So like if you have a lot of light curves, what happens is it once you divide it, it runs much faster on like a multiple number of your CPUs instead of just running them one by one. And that's where you can see the true beauty of parallelization. So one more thing to know is that this long scale periodogram, it takes O of the n square time complexity. Now, what is time complexity? Time complexity is something that we basically use in computer science to check how we can characterize the time it takes to run a code. So let's say I have n cakes and I want to eat n cakes. If I pick them one by one and eat n cakes, what is the time that it would take me to eat all the cakes? It would take an n number of tries to eat all the cakes. So the time complexity of me eating the cakes is O of n. Big O is just the notation of what the time it takes. So Similarly, let's say some process allows me, wants me to go to a step 2 times. So then I'm going to I'm going to eat the cake once and then twice, and then take the second one, take one bite, take the second bite. For this, the time complexity would be O of n squared, intuitively, because you're doing one process twice, you're doing the second process twice, and you're doing the third process twice, and you're doing n process n numbers of n 2 times. So like you can like just go from 1n to n, and then the total time complexity would be 2n if you go through that n number of times. So like you are going through that once, you ate 10 cakes, then you're going through that the second time, you're going through that the third time. If you go as many times as the number of cakes there are, then your time complexity would be n squared. Similarly, the classic long scale periodogram has a complexity of O cross M, where n is a number of data points and M is a number of trial frequency. So if you imagine like n and m are almost similar, then the time complexity of this is often can be thought of as O to the n square, if you think n and m are the same numbers. What happens in parallelization is that we divide these n square terms to p processes. So like instead of just using one process, like one person eating the cakes, there are multiple people who are eating the cakes, different parts of the cakes at the same time, and the goal is to eat all the cakes. So if you look at it, then if you have like p people eating the cakes, your time complexity reduces by a factor of p, which you can see as is in the case of the parallel when you like use p processes to parallelize the cakes. So let's move to does anybody have any questions about what I just said? Any questions so far? Please feel free to like unmute in the middle and ask me if you have a question. If not, we can move ahead. All right, no questions. So now we will look at how we can actually implement this parallelization process on our CPUs. So parallelization on our CPUs can be achieved through two main steps, either by using something framework called as OpenMP or Open Multiprocessing, or by using MPI, which is Message Parsing Interface. The downside to OpenMP is that it cannot run in Python. Because it cannot run in Python, and we are basically doing this workshop in a Python-oriented manner, we'll have to look at a C code, but don't worry. There's like a complete explanation of the C code which is given below. So first, I'll just explain how OpenMP works, and then we can look at the C code. So OpenMP uses shared memory parallelism. So in shared memory parallelism, if you have like 10 cores working on the same thing, so 10 people are working on the same thing, they are getting paid by the same person, if you think about it like that. So all of these 10 people share one common interface. So let's say there's a bank that everybody gets money out of. That's how you can think of about shared memory parallelism. And in the real case, it's like a bunch of CPU processors which are using the same memory pool. So let's say you have 128 gigabytes of memory in your HPC, then all the 10 processors are sharing this 128 gigabytes of memory. It also enables multi-threading. So even in CPU cores, you can have multiple threads, so that like different processes that can like calculate stuff. You can think of threads as like that. So in our CPUs, it enables multi-threading, where each thread or each process that you are running. So a thread is a process that does the calculation for one light curve, if you can imagine it like that. Then it has access to the same memory space. So like all the different CPUs, all the different threads on those CPUs or different processes on those CPUs are using the same memory space for OpenMP. And therefore, it is ideal to use OpenMP for like multi-processors on a single node. So if you like just have access to one computing node, as you learned before yesterday, what a computing node is. Computing node is a node that allows you to basically access resources on an HPC and on your jobs. If you just have like one computing node with a couple of CPUs on it, you can access it by OpenMP, and then run your multiple processes on just one computing node instead of like using many if you don't have access to those. Here is some introduction to OpenMP. You can go through that, and then you ask why doesn't OpenMP for Python exist? OpenMP is not supported for Python because multiprocessing is a higher level tool. So like multi-threading and multiprocessing is different in Python. And that's why you cannot have OpenMP for Python. But there are other Python tools that use similar logic. Uh, so like if you're just using Python, you can use something called multiprocessing. If there are any questions for the same, you can look at it and ask me later. So um, there's also something called nested parallelism. So let's say you have one task which is assigned to one core, and then it nests into two different tasks, and then again. So you're just like basically like creating branches of smaller tasks in your parallelization code. And so if you want to think of it, you can like imagine where a thread is basically working on a light curve, and then for each light curve you're basically just implementing like smaller sections of the light curve and then like integrating it into the final result. uh, SIMD, we talked about yesterday as well in our in the introduction section, and like where you have single instruction and multiple data. So like you just give one instruction which is to basically analyze the light curve, and then you have a lot of light curves which like work on different data elements. And then if you just like uh, if you just basically did what you did in the NumPy example. So instead of just like adding numbers from like one by one, you just take the entire array and then add it in one go using C. That's what exactly vectorization means, as I explained in the last section. And we can also do one more thing. We can actually offload some tasks from CPUs to GPUs. GPUs are extremely well developed for parallel processing. This is just a precursor to what we'll learn in the next episode, what Alex would teach us. So for this, all of this CUDA, OpenCL, QPy, and PyTorch, we'll cover in the next section. So let's look at an example now. So let's say you just want to run a loop in parallel instead of using it in serial by using OpenMP. So if you look at the Python code here, if you look at the C code here, you basically have header files. .h stands for a header file. A header file is something that you can think of as a Python library. It is a bunch of code that's predefined that allows you to do stuff in C. You can think of it as an equivalent to a Python library. So, and the omp.h or the OpenMP header file allows you to access functions from OpenMP. So it basically allows you to do the parallelization using OpenMP. In this example, what we are doing is we are basically using three arrays, and for these three arrays, we are just learning a loop where for n size of the arrays, which is like 100,000 here. So we are taking arrays of 100,000. Each array is of the size 100,000, and then we're taking two arrays, and then we are adding it to a third array. That's what we are doing using the C code. And for this, the Bn, Cn, and An are sizes of array n, arrays of sizes n. And first, in C, we have to basically assign a memory to it already. Now, what is memory allocation? So you basically tell the C processor how much memory or how much size would the array have. So when we do this initialization, we are already telling C that this array is of this size. And then we initialize them. And then this is the step where we parallelize. So using this function for OpenMP, we basically split the adding of the arrays into like smaller sections. So like this will take care of the first half, this will take care of the second half, or first 1, 4, 2, 4, 3, 4, 4, and the last one. And by doing that, we can basically parallelize our addition of the array, and then everything would be gathered in the end. So like all of the results would be appended together, and then we'll have the final result, and then we can print to see how it comes back. you can also look at the Python equivalent of this, and please feel free to ask if you don't understand anything or if something is missing for you. So the Python equivalent of this code would be just like defining a function that adds two arrays. As we saw in C, we have to specify the size of the arrays before. So like we initialize the arrays to be of n size. Here we are asserting the same because we want the B and C array to be of the same size. As you are adding B and C, your A array should also be of the same size, because if not, then you will violate the way you like assigned it to the memory in C, and which is why the Python code also has the same kind of syntax to make you understand how C works. Uh, then what you do is then you again create an output list, because this is what you do in C as well. So like even you have to specify the output list first, like you have to initialize it, and then you are just looping through the number of times that you want. So like n here in our case is 100,000, and then you are just like looping it over for 100,000 times. And but because we are using parallelization, it will be split into smaller chunks. And again, you can use it for 100,000. You can initialize the B and C arrays, and then you just use the function add arrays. And this is what the C code basically does. Are there any questions on how the C code worked? Or like if there's any question about how parallelization works, or like how we implemented the C code? Okay, there are 4 questions in the chat. Okay, okay, nothing. Are there any questions for the same? Because in the next step, you'll have to do an exercise for which I'm going to give you 10 minutes or like 5 minutes. 5 minutes is enough, I guess. And uh, you should be able to, okay. Without looking at the solution, can you just type yes or no if you think you can parallelize this loop? I'm giving you 5 minutes to think about it. You can have a look at the code. If you don't understand anything, please let me know and we can cover that. All right.
Hi, I have a question.
Yeah, sure. Go ahead.
Yeah, so in the above example where you assign the directive for parallelization, can we
Yeah.
understand from there how many chunks are parallelized for the given number of processors that we have?
So here
Because
what
looking from
happens is,
here, it looks very opaque. It doesn't tell me like how many arrays, how many elements are passed to each processor.
yes. So what you can do is you can basically this works by basically looking at what your CPU or that already has, and then it uses the optimum condition for that. But
Okay.
if you want to know it in detail, I can send you the resources that you can look at and understand how this works, like in detail.
Yeah, that would be great. Okay, thanks.
Yeah, no worries. Currently, it just looks at the optimum condition for your PC or your local machine, and then it decides on how many it wants to take.
Yeah, I think I get this point. Yeah, okay.
Yeah. So take 3 more minutes and let me know if you can parallelize this loop using OpenMP. If yes, like you can just write yes or no, and if you want to add an explanation, feel free. All right, folks who joined in later, are you guys logged into Bura? Because after this exercise, we are going to be running one code on Bura. So if you guys are not logged into Bura, log into Bura. Just go at the section that is here. You go to section 2. You initialize your Python virtual environment, and you load these modules also while loading your virtual environment. If anybody has a problem, please type it in the chat, and I think the instructors would be happy to help you out with that. Because currently we are going to be implementing the next section that I teach. We will be implementing the code for that in Bura. So I want everybody to be logged in and like load and have every module loaded so that we can just directly run the code. Also, yeah, I think this is enough time. Can you guys paste your answers in chat? Like, can you parallelize this loop or not? And if anybody is feeling confident enough to basically argue why yes or why not, please feel free to unmute yourself and let me know. Yeah, Riley, go ahead.
Yeah, I think the answer is no, because unlike in the previous example, this is a cumulative sum, which depends on the iteration of the array of the previous element in the array. So I think that like the way OpenMP breaks it into chunks won't work in this case.
Yes, that is exactly correct. Thank you so much, Riley. So did everybody else follow what Riley said? Can you just put a thumbs up if you understood what Riley said? All right, I think we are ready to move on to the next section. So now we'll look at
Meet, I'm sorry, Angelica, just to ask you, for example, in mathematical sense, if it is like a recursion, then it is not possible to parallelize.
If
Is it some kind of equivalence, for example? Not too,
yes,
too much.
No. If you think about it, it's like this. If you can split the task that you're doing into smaller chunks, then it's parallelizable. But if your first state is dependent on the end state, how you're doing it in this sum. So like you're doing a cumulative sum, right? So your first state is also dependent on the end state.
Yes, that is recursion.
That is
Mathematical recursion.
Yes.
So
Yes.
recursion in
So you
mathematics
cannot
is difficult to. Okay, thank you.
Yeah, Alex, go ahead.
Yeah, I just want to add that I think that I'm not a mathematician, but in many cases when we have a recursive problem, at least when it is like pure mathematics, we can think about a smarter algorithm. So usually if something is non-parallelizable, it doesn't mean that it's going to be a bottleneck, but it means that you have to think further than just splitting things in chunks and maybe look for the right equation. So it is traditionally the first thing that is recommended in optimization. Look for smarter mathematical formula, but usually people are doing it in the opposite way. First we parallelize, then we find the chunks that are non-parallelizable, and then we start thinking about how to do it in a smart way.
Thank you, Alex. I think that it is really important. The math. Thank you.
Hi. So I also wanted to like say a few words. So
yeah, sure.
In this example, we don't want to go beyond the scope of this example, but what the question is asked, if each iteration takes a lot of time, then one can store the result of each iteration via communication. Even if things are parallelized, you can at some level you can store the array and ask one processor in the end to process. So I was just wanted to tell her. Yeah.
Yeah, sure. No worries.
Yeah.
Thank you, Navid. All right. Let's move on to the next one. So the other approach to parallelize things for CPUs is by using MPI or message passing interface. So in comparison to OpenMP, MPI uses distributed memory parallelism. So how do you understand that? Instead of having a bank of memory where each processor uses in like as a vote bank, instead of that, each process or each processor is given a portion of the memory. So when you are basically dividing your processes into chunks, you say this processor is doing this chunk, then it will allocate it a certain amount of memory. This processor is doing this chunk, it will allocate it a certain amount of memory. So let's say if you have like 4 processors and you're using 64 gigs of memory. So for each of the processor, you will basically allocate 16 gigs of memory intuitively. But that can also depend on how much consumption each node has or like each process has. If the splitting is not uniform for your basically the chunks that you are splitting it for, all the processors are not uniform, then it may not be distributed as that as well, as it determines like the optimum memory required for that particular core and then distributes it in that. Again, this is some history for MPI. Please feel free to go through that. And so basically what MPI does and what I just talked about is that MPI basically copies a program. So like if you have 100,000 night curves, it will like copy some of the programs into like smaller chunks for each of the processor to run through. And like each processor that's running your code has a unique rank, right? And all of these ranks basically communicate with each other while working and like while plotting the results. And then you can use just one final rank to basically combine everything and give the final output. So each rank is so just to give you a visual of how it's happening, you have one process that you want to run. It gets divided into smaller chunks to different CPUs. These CPUs have different cores which like are subdivided, and for all these subdivided CPU cores, each core is called a process, which is like executing a process, and each core is basically given a rank. So the first core that is running the process is given the rank 0, and then the rest are called 1, 2, 3 to n, however many number of cores that you're using, right? And for all of these ranks, they're communicating with each other. So it's not like you just made a copy and you passed it to one and the other is completely independent of what this is doing. They all know what is going on with every single node. And for each node, then you have basically a communication interface through message passing, which then basically allows all of them to talk together, divide it into proper chunks, and then give you the final result in a much shorter amount of time as it would take just one CPU node to run. So let's look at an example to make this visualization more clear and like more apparent on how that works. So you can use MPI in Python using the MPI for Py library. And what you do is you first basically, when you are using MPI, you basically choose a number of CPU cores as well as the number of CPUs that you are allocating for your job or your code to run. So when you do that, each CPU and each core needs to communicate with the other. So for that, what you're doing is you first need to set a communicator. And for that, you first like basically MPI sets a default communicator, which is using the mpi.com world command. And then basically you are getting the ID of each core. So like if you have like one process, you divide it into multiple CPUs. Each CPU would have their own core in which the copies of the program are there. Each core is given a rank, right? And then you can also like if you just want to check how many like total copies are there or how many like individual CPU cores are running this program, you can get that through using the size command. So you're just like communicator.get size, which basically gives you the total number of CPU cores that are available. After that, what you're trying to do with this is we are trying to basically calculate the rank squared. So like let's say you have six different CPU cores that are running. So like you divide it into 3 CPUs and then you have 2 cores for each CPU. So what this will do is that it will take the rank of each core, which is starting from 0, 1, 2, 3, 4, 5, and then give you the square of each core. Does that make sense to everybody? All right. And from that, what you're doing is once each core processes its own thing, you can yeah, Alex, go ahead.
Meet, there is a question in the chat from Rachel. Rachel, do you want to read it?
Hi there. Yeah, I just didn't want to interrupt the flow. Me, I had a question. You're talking about rank, and the exercise, and the word rank can sometimes have a connotation of priority order. Is that the case here, or is it really just being used as an identifier?
As an identifier, that's it. There is no priority. That's like you call the 0th rank the root process. That's one thing, but
Okay.
it doesn't really have any like priority over all the other ranks. You do call the 0th rank the root rank. That's it.
Okay. Thanks for clarifying.
Yeah. So like the root, which is the 0th rank, it's called the root process. The other ranks are just called like separate processes. So what you're trying to do here is you're trying to print the squares of each rank, and then basically you gather all the data. So like each rank would calculate its own square, and then all the squares would be calculated by using the communicator, which will use one more rank to use. So like if you have like 4 ranks that are calculating your result, you need one of the rank to do more work in order to gather the results, because you need to run the gathering process somewhere. Usually what people do is they use the first rank. Rachel, I think this will add to what you just asked. Usually it is the norm to use the first rank or the root process or the 0th rank uh, to basically gather all the data from all the results, and then basically print it out. That's the only reason I think we can say that the root process is given a special name, because people generally use it to like gather all the results, right? And we can also basically, it is a norm for the root process to get the results, but it doesn't have to be like that. You can use other processes such as like rank 2, rank 4 to just gather all the results and print them. It's just like people use the 0th rank to do stuff. If you can see here, we have defined the if rank is 0. It doesn't have to be. You can keep it as any rank. I think, Rachel, that clears out all of your doubts. Like,
Yes, that was very clear. Thank you, me.
all right. So as you can see, if you just use 2 CPUs and 2 cores for each CPU, so which is 2 and then 2, so that will give you a total of 4 processes and 4 ranks. And if you just like run this code using an HPC, then this is the output that you will get. So rank 0 will compute 0 square, rank 1 is 1 square, rank 2 is 2 square, and rank 3 is 3 square. And then you will get a list which is 0, 1, 4, 9. If you still have any doubts, like with the explanation of ranks, communicator, gather, like just gathering the results and like how we're communicating, please feel free to go through the terminology, like, and please ask if there are any questions. Now, I want everybody to open up your Bura. All right, does everybody have their Bura open? Bura system open? I want all of you to do one thing. I want all of you to get into mpi_example.slurm. I'll type it out in the chat for you guys. I want you to perform this command. Okay. Are you guys able to access this file, please just type yes in the chat if you are on your Gura system. I can see Marcus, Riley, and Alex are able to do it. What about the rest?
Well, essentially, the instructors can do it, but everyone else needs a little bit more time. Let's wait for a couple of minutes.
Yeah. Yeah, Fatim, that's the output. Yep.
Thank you.
All right. I still wait for 2 more minutes for everybody to just be able to do it. Antonio was able to do it. Kieran, home, where you guys, Marcus, were you guys able to do it? John? All right. I think everybody should have been able to do it by now. If not, you guys can just, okay. Yeah, Om was able to do it as well. Karen, Marcus, are you guys facing any issues? If you're facing any issue, just speak up and I'll be able to help you out. Karen was able to do it. Marcus? All right, Marcus was also able to do it. That just leaves John. John, were you able to do it? Yes, I know there is an issue. Some people keep getting logged out by web, but it should be fine. You can just log in again and try to run this. Yeah, so I think everybody was able to basically just look at the file once. So we're good to go. So I'll explain what you saw in the file first. So all of you had a very good introduction to Slurm yesterday by Gordon. I'm just going to remind you of the basics. So the bin bash basically asks the Slurm to use to execute commands on the bash, which is basically the terminal. The first Slurm argument that you have is your job name. So basically whatever you want to call your job, you will specify here with the J tag. The second one is this is called a flag. So whenever I'm referring to this -j -o -e, these are called flags. So this basically signifies the output file, this signifies the error file, and this signifies the partition that you want to take. So if you just want to run a simple parallel job on Bura, that's the partition is called computes thin. If you wanted to do a GPU job, your partition would be called GPU, which you can again check by using sinfo, as you were taught yesterday. So the next thing to know is this is the number of compute nodes. So how many total nodes that you want to access, and n is 24. So the total number of CPU cores per node. So let's say if you have two compute nodes and there are 24 cores per each compute node, you will be using a total of 48 MPI processes. Can anybody tell me what would be the maximum rank in this case? Anybody from the participants? If you would like to just tell me what would be the maximum rank in this case. You can guess, that's okay. I just want this to be an interactive session. So if you guys can just like tell me what would be the rank in the case that there are a total of 48 processes.
24, 48, I think.
No, as I said, the rank starts from 0. So the total number of ranks would be 47.
Correct.
Yes, that's correct. So so now let's look at how we can actually implement this Python script using MPI on Slurm. So again, we'll ask the terminal to basically have like the bin bash command, which is basically executing our code on the terminal. We have the job name, output file, error file, partition. And here we're introducing something new. Like instead of using this n, capital N and small n, we can basically specify how many tasks we want to run. So you're requesting 2 nodes and then you're requesting 4 tasks. So this will basically run 2 cores on each node. So you'll have basically a total of 4 tasks or like 4 processes. You're specifying the time. You can specify the time for how long you like the maximum time that you want the job to run for. After this, the job will automatically end, even if the code is not run. The last thing that you need to find is the memory, right? So you specify the memory that you want to allocate to your job. And then just for sanity checking, this will print the list of modules that you loaded at the start of the session. This will be visible to you in the out file. So what you want to do is once you run this code, you will have, when you do ls -l, you'll be able to look at the a file called MPI and then the Slurm job name. So like a code is assigned to your Slurm job, which you saw yesterday, .out. And then you want to cat into that, and then you'll see the list of loaded modules that are there. Again, for sanity checking, we are also activating the virtual environment. And then this is the most crucial part. So like how to run like Python scripts using MPI. So MPI has a special syntax called MPI run, which is the executable for how like using MPI for a Python script. NP stands for number of processes, which we kept to 4 as n tasks and R4. And then you just basically run your Python code in the normal way you run a Python code, which is Python and the name of the Python file. Now, what I want everybody to do is I want you to do sbatch MPI example.slurm. I pasted that in the chat, and just you just need to copy this and run this in your HPC and on Bura, and just like give me a thumbs up or like type yes in chat. In fact, I can also do that for you guys. I can also do that on my PC so that you guys also can follow along with me. All right, let me switch my tab to Bora and see what's the problem.
While Meet is dealing with this, the problem is probably that it was copied from somewhere where there was stop signs. So try to go through the break lines and spaces and just like remove them and enter manually spaces. It should fix it.
Yes. Just open it up.
Meet, we still do not see your screen, by the way.
Yeah, just a second.
Okay.
All right, are you able to see my screen now? Let me know if you are able to.
Yes, we can see it.
Think that there's supposed to be a problem in the comments. Probably. Let's see. If I just write this out. Yep. And then exit. And then I do S patch. I just also need to save. Then let me run this. MPI example Slurm. Can check it using SQ. It is in pending. All right, Marcus, do you want to share how DOS to Unix would help? If you'd like to do that, then go ahead, please.
Sure,
You can
no
stop sharing.
Yes, let's see if that works. Let me briefly share the Bora connection here on my machine, probably this one. So if you're having, unfortunately, one of these nasty Windows and DOS files, then you can get and update this by calling DOS to Unix and followed by the respective name of the file that you'd like to update. And this is a Unix command that will update this and changes it in place and updates everything with these characters that are giving us headaches. And then you can just submit your job with S batch and you're good to go. That's all. And this saves you from the trouble of figuring out which of the characters that you could with cat minus e do are actually the culprits here.
All right. Thank you so much, Marcus. I think everybody can, if you can just also, yeah, you already pasted it in the chat. So if anybody else is having problems, you can just run that and then do a patch, and then you'll be able to see the output for the code, which in our case would again, is everybody able to see the workshop materials now?
Yes.
Yes.
Yep.
Yes. So when you execute this Slurm script, the output for us will be this. You will basically get just a list of 0149. That's what you're going to get. This was just one way to start like working, like implementing code using Slurm on the HPC. And I would also like you guys to now take 5 to 10 minutes to just to go through these exercises and try implementing them by saving them into a Python file using Nano. And if you want to just use the solutions, then both the Python files are already attached with it. So the first one is called mpiex1.py, and the second example is called mpiex2.py. You can get into them. You can look at how you can implement these things. And then there is also this Slurm script that you can use to run this. You just need to change the Python MPI example to MPI EX1 or MPI EX2 in the same Slurm script, and then you're good to go for your exercise code. So you guys can work on the exercise till then. Does anybody have any questions about what I've covered so far? If there are any questions, please feel free to ask me. If you have any questions with the exercises as well, please let me know, and I can help you out with those as well. Does anybody have any questions? If not, you can go through the exercises, and if there's any doubt, please feel free to reach out to me. Alex, you're teaching the next session, so I think let's get started. Would you like to go through that?
Yes,
Yeah.
considering that we are slightly behind time, first of all, thank you, Meet, for the great first session, two episodes. Yes, so I suggested we first go through the next episode, which is on GPUs, and then we will make a break. Since we do not have GPUs available on Vura, I will share my screen when I teach you the code examples, and I will show how you can at least try them on Google Colab. Or if you have NVIDIA GPU on your laptop, I will show you what you can do to try this stuff on your laptop. But there will be no exercises for you during the session because obviously, I mean, what if you don't have a GPU? So yeah, let me share my screen and let me start talking. Let me first of all move it to another monitor. Okay. And let me share my screen. Okay, I assume you can see this. And in case there are questions, please feel free to unmute and ask them directly because I don't have the chat in front of my eyes anymore. So yes, what about the GPUs? Now, I think that everyone at least heard something about GPUs because we are living in 2025 and because AI is everywhere, from every toaster and from every coffee maker. We hear talks about AIs, and AIs mean training on GPUs. But what are they and why they're important for the modern science? So essentially, GPUs are highly specialized processors. If we have a CPU in our laptop or in our PC or in a supercomputer, then CPU is a computational unit that is highly versatile and can perform almost any imaginable operation that exists in programming languages. So because it is so universally applicable, it cannot be optimized for only one task. GPUs, on the other hand, were developed for very specific tasks for handling image processing. So for either graphics or for different types of gaming. And in the 90s, when they were developed, it was their sole purpose, processing images with high speed, which is essentially, if you have a video, then you have lots of images that you have to process like 24 frames per second. If you have a game, then you have to do the same stuff, only you usually also have calculate something in the background to generate this image. And this is how GPUs were developed, and they were optimized for handling matrices because any image is essentially a 2D matrix. Or if we are talking in a more scientific languages, it is a tensor, two-dimensional. Now, turned out in early 2000s that actually tensors and matrix operations are very common in many scientific applications. And then NVIDIA decided, okay, so let's give people a direct access to the inner working of the GPUs, and let's see whether it can be adapted to some other purposes. And that was a turning point and a very important milestone to the modern processing, because turns out that a lot of stuff can be converted to matrices. If you do some graph operations, if you do some complicated equations that are like needed for modeling of air flows somewhere, if you utilize some pretty smart math, you often can find a matrix representation of a lot of mathematical problems. So GPUs turned out to be very usable for this kind of tasks, and this is how general purpose GPUs were created. So let me increase my screen for a little bit so that you saw this better. What is the difference between GPUs and CPUs? So CPUs usually have several cores, so 4 cores here, but it can be like 16, 32, I mean, 128 is something extreme, but I believe such CPUs also exist. And each core has its own level 1 cache, its own control that determines how the information flows back and forth within this core. So each core is a mini processor that handles a lot of complicated things inside. Then we have level 2 cache and level 3 cache, and the cache is essentially a small amount of very fast memory. So each, as we go through the levels of cache, the memory gets faster, but the volumes of those cache are usually getting smaller. And then outside of the processor, we have our ordinary RAM, that is actually where we store all the information accessible to our computational unit. So when we are talking about GPUs, the architecture is a little bit different. We have thousands of small computational cores that do not have this complicated inner life, and that have only a small amount of cache and relatively simple controlling units. These computational cores, so essentially each thread, well, not thread actually, we will be talking about terminology a little bit, but each row in this scheme has its own cache and has its own control. So essentially, each processor does not have its own personal cache. And then this whole system of computational cores, it has one common cache, and then it has a dedicated memory. So you may have heard about integrated and dedicated GPUs. So dedicated GPU is actually something that is not integrated with your motherboard, and these GPUs usually have their own dedicated RAM, which is different from the whole RAM of the computer. And the volumes of video RAM and the volumes of the caches are important because they affect how much bottlenecks are there in the graphic card and how quickly we can load and upload and unload chunks of data. And it's not the performance of the graphic cards isn't only about how many cores you have. It is also about how it is organized and how much of this cache and video RAM memory you have, because it determines how quickly you can exchange data with your processor. So these differences in architecture explain the differences in performance. So CPU can do a lot of complicated operations even within its core, but GPUs can only take a matrix, dedicate each unit to dedicate each chunk of data to one core and perform the same operation on all of these cores. So as a result, we have a lot of versatile in terms of the functionality cores on CPUs, and we have thousands of simpler cores on the GPU. And the default mode of performing of sending data to CPU, you can just create most of the programming languages were developed for working with CPUs. So if you create a variable, it goes directly into your ordinary memory. And if you try to perform some operation with it, it's by default, it is believed that CPU will handle it. So it will go to the CPU cache and it will be sent to the cores. GPU isn't like that. You have to directly say your computer, send this chunk of data to the video, to the graphic card, and do something there. This is why most of the programs that utilize GPUs actually have two parts. They run both on CPU and on GPU. CPU is responsible for processing the data, for deciding what to do it, and for sending it to GPUs together with instruction. And then GPU just says, okay, I need to multiply each pixel by 2. This is what I'm doing. This is very simple worker. It cannot handle much complex operation. So in 2000, NVIDIA decided, okay, let's give people access to all those possibilities the GPU have, and they issued a programming language, or a platform rather, called CUDA, Compute Unified Device Architecture, I think, yes, which allows direct manipulation of the data that is being handled to GPU. So originally CUDA was a programming language on its own, and now there are wrappers and interfaces in multiple languages. Primarily, this development still goes in C language, but in Python, we can also deal with CUDA directly. And in order to understand how to write a program on CUDA, we have to go a little bit deeper into how GPUs are organized hierarchically. So when we have a piece of code to be run on GPU, we call it a kernel, CUDA kernel, which is effectively just a function that is going to be executed on GPU. Then there are different aspects to the hierarchy of GPU. I think it's better if I try to explain it to you on the picture. So we have two aspects. One is physical organization and another is logical. Physical is how those cores are organized into a GPU. We have single core, which is a simple, the most basic computational unit. And these cores are united into streaming multiprocessors. And each streaming multiprocessor has its own fast memory that is shared by all the cores. And it has its own controller that schedules the tasks for the cores. So each core can perform one task per moment. And the normal thing to do for these cores is that they are all performing the same kernel, the same task, but on different pieces of the data. So when we send something to the streaming multiprocessor, we have some memory for the data that is then being distributed across the cores. And we have some memory for the instructions that are all the same for each core. And then these streaming multiprocessors are united into the GPU. Now, how they are united is separate thing. It's not so simple to actually describe, but what is important to us is that CUDA provides us with a logical counterpart to this hierarchy. So the logical counterpart goes like this. Each core can execute single thread. So thread is a stream of instructions. So if we have a kernel, which is a function, I mean, there is a lot of terminology that has counterparts in traditional programming, but it's specific because these things were developed in parallel. So each thread can execute instructions one by one, and each thread runs on a single core. Then these threads are united into blocks, which roughly correspond to the streaming multiprocessor, but not exactly, because actually we as users, as programmers, we can define how many threads can be assigned to the block. The limiting amount of the threads per block is defined by the physical architecture, but you can assign, for example, a lesser number of threads per block. Sometimes optimization for GPUs means looking into the hardware specifics of your GPU and figuring out what is the optimum numbers to unify, optimum numbers, optimum configuration for these blocks and grids. So grids, blocks unify the threads that share the memory, and then blocks are unified into the grid, and this grid can be one-dimensional, two-dimensional, or three-dimensional. Obviously, it's not like there are some streaming multiprocessors that are being reshuffled physically on the GPU. So it is purely a logical configuration. But this logical configuration can be convenient when you are solving different tasks. So for example, if you are processing images, it is often convenient to work with a two-dimensional grid. If you are doing some three-dimensional simulation, obviously three-dimensional simulation can be more convenient. So when we are a question, do we really need to know all this? Actually, if we are doing some low-level programming for CPUs, its inner working is even more complicated than this, but it's not like we are spending time actually figuring out how to send each piece of data to a specific computational unit in CPU. I mean, normally, sometimes we do, but it's not common. So it depends on your task. If you are using one of the higher level libraries, so for example, if you ever played with machine learning, and if you used something like Torch or TensorFlow, you may be okay without knowing this stuff. But if you are doing optimization on a very low level, if you have some massively time-consuming task and you want to optimize it as much as possible, then you may need to go to the tools that allow you optimization on the level of threads and on the level of blocks. And we will look at one of such libraries in a few minutes. And another thing why it's important to understand is that even if you use some higher level libraries, actually a lot of parameters of these libraries have connections to this inner working. So once again, if you ever tried to develop some kind of model on Torch or TensorFlow, all those numbers that define the parameters of the layers and of the sizes of the batches, they often have connection to this inner architecture. So we are still, I mean, because CUDA development is still not as mainstream and GPU software development is not as mainstream as CPU software development, sometimes you still have to understand how it works under the hood. So as I mentioned, a normal program that utilizes GPU is composed of two parts, I mean, three parts if you want. We have host code, host means CPU, where we are deciding how to manage memory, how to process data, and where we are defining our original function. And this part of the program sends the data to the GPU. Now, GPU itself performs simple operation on each of its cores. So essentially, all the GPU code is in one way or another tensor multiplication or tensor operation more broadly. And then we have figured out the memory management, which is effectively also performed by CPU, but it is the communication between the GPU and CPU. So CPU actually have to directly say GPU, allocate this amount of memory and then clean it. It does not happen automatically. So there are number of libraries that can do this, that can work with CUDA on Python. High-level stuff is these days quite often machine learning. So if you ever work with PyTorch, Keras, or TensorFlow, this is it. And lower level are things like QPy, which is somewhat analogous to the NumPy library, or even Numba, which allows you to do quite custom tailoring of your functions, and that actually handles the transformation of the functions that you've written to the CUDA digestible form. So let's do a little bit of examples, and let me figure out on which platform I'm showing it to you first. First, probably let me show you the how you can do this stuff in Colab. So let me switch my screen sharing to a different window. To this one. Okay. So you should see the Google Colab interface. So I hope that everyone is familiar with it, but if not, then Google Colab is your thing to check. If you have Google account, then you can use it directly. I already have a Colab notebook open. So by default, your Google Colab is connected only to CPUs, but you have access to the GPUs in some limited amount. So if, for example, right now I say Numba, import Numba, and try to execute it, it will probably execute this stuff. It will probably try importing it, but it does not mean that it has access to any CUDA. So we can check whether we have any CUDA stuff available. Actually, I will do this from Numba. Okay. We can do it like this. We already imported Numba. And let's see if we have something available. Let me move this here. Okay, it doesn't have module CUDA. I wonder if it's because we have done this import with only CPUs. Let me try this. Okay, can you see it now? False. Okay, so what does it mean is that there is no GPU connected to this kernel, and CUDA is not available in this case. Now, how we can connect the GPU? In the runtime, we can choose change random time, and here we can see few more possibilities for the accelerator. So accelerator means computational unit. By default, we have only CPU, but we can switch to the GPU. Yes, we are disconnecting and deleting previous runtime, and we are saving this. Now it is connecting, so it says that it is connected, good. And let's see whether we have CUDA available right now. True, great. So now we have CUDA capabilities here. Now we finish that even if it is available, when I try to run the number episode, number example from our episode, it got some errors related to the wrong version of the library. The TensorFlow example, so actually let me move it here. Okay, you can see it again. So while we can check that CUDA is available, if we try to execute this stuff, you will get an error during the execution of one of the functions, probably. There might be a hack. I mean, you can install a different version of Numba, but I didn't do it in advance, and I don't want you to do this now. So actually, instead of this, I will show you the Numba example on my PC. The TensorFlow example should work all right, and you will be able to try it. The Torch example should be all right, and you will be able to try it on Colab. But for the Numba example, let's switch to my laptop view. And let me move Windows once again. It is not that simple to navigate all those windows. Okay, let me put this here and the terminal window here. So I already have an environment when I have Numba installed. So I will activate it. Is it Numba? No, it is InterPython. Good. And I will do this in JupyterLab because it will be a little bit more educative to show you how we can do it online. So we are creating a notebook, and then we can try our examples. So let's, our example is already something that we already talked about. It is summation of the vectors. So we will try to do this on a low level with a low level library, Numba, and then this higher level library with Torch. So things that we have to do in order to run it, first we need to do the import. We have to import Numba. We will need NumPy. And I don't remember, we probably don't need OS, but we will need time because we will want to measure this. Okay, so we imported this stuff, and now we have to define, to figure out how to create those arrays. So since we are doing this, first of all, since we are writing the CPU part of the code, we have to define the data. So let's decide that we want to sum two arrays that have size of, I don't know, 10,000 elements, and we will use two NumPy arrays. We can do this with list, but with NumPy arrays, it is a little bit more native, because if you are going to do any kind of HPC computing, you are probably going to be using NumPy. So we can do, let's say we will do the floats, but we will use float 32 to reduce the size of those arrays. instead of float 64. And we will do we will create A and B array. And then we have to create the array of the same size. So we could use alike, or we will do zeros like of the same size as A array. So now we have 3 arrays. Yeah, something, and with float values. Now we can figure out how do we convert. So obviously, with the sizes like this, we could easily run this on CPUs. But how do we do this on a GPU? First of all, we have to give our computer an instruction how to convert this stuff into something that GPU can consume. Because if we will try to pass NumPy arrays as they are, CUDA won't be happy. CUDA won't understand what is this format. So fortunately, this CUDA module, and it does not here, this CUDA module has a function that will transfer these arrays into the right format for us. So we will say UA, and we will ask something to device. Good, it is suggesting us this. And we will do the same for B and for C. Okay, except I have to correct the names of the arrays. All right, this works. Now we have to define the parameters of this CUDA grid on which we are going to do the computation. Now, what are those parameters? It is the number of threads per block. So essentially the number of these logical units that correspond to the cores that will be executing the same command, but on different pieces of data. And then we have to configure the number of blocks per grid. And although those things have rough counterparts in the physical units, actually we are deciding how many threads per block and how many blocks we are assigning. So later on, I encourage you to play with these numbers and figure out whether it affects the performance. So let's say thread num is going to be 2056. Usually there is some limiting number on this. It is related to the number of cores that are assigned to a single multiprocessor. So often 2024 is the limit for this case. And then we are going to define the blocks num, which is, okay, so here we are going to use, actually I will even have a peek into the materials because I do not remember this equation. Yes, so here we are going to use this formula because we will need to figure out how many blocks are going to be allocated in this grid. And we have to keep in mind that each element of our data has to be assigned to a single core, to a single thread. Now, the thing is that in principle, you can assign more threads. You can create more threads than you have physical cores on your GPU. But then you will not be able to execute all the threads at the same time. So what GPU will have to do is it will have to, once again, split those threads in chunks, first load the first portion of the threads into cores, execute it, wait till all the cores finished executing, unload the results from the cores, and then load the second part. So in practice, since every movement of the data is an overhead and increases the time, it is better to create the number of to figure out how many threads is possible to execute on your GPU in one go. And it's good to synchronize those numbers between the numbers of the threads and between the number of the cores on your CPU. So, okay, since I used a different names here, I will actually type it manually to not mess up. So, we are going this like this. And then we will do the integer divide in order to have an integer number, because we cannot have a float number of the thread. Okay. Now we can, we have everything prepared for loading the data to the GPU. We have the configuration number for our kernel, but we are still missing the functions that will be executed on the GPU. So let's define the function. Let's call it addVex, and it will take all the 3 vectors as parameters. So the vector that we are going to sum and the vector that is going to store the result. We have to decide, we have to configure the grid. We already have the numbers for configuring the grid, but we still have to calculate the thread ID that will be taken each element of the array. So once again, threads can execute the same commands on different chunks of the data. We have to figure out which chunk of the data will go to which thread. So we have to get the IDs of the threads, and we have to assign them to each vector element. So we can do it with this command. CUDA grid already has the specifications of the grid behind of our GPU, but we are passing this parameter single one that essentially says us the dimensionality of our grid. So we are doing this in one-dimensional grid, so we are passing 1, and now we are checking that as long as the ID of the thread number of ID is lesser than the size of our array, we can execute this summation element-wise. So the element of our result array is going to be the sum of the corresponding elements of the original array, like this. So when if we would execute this on CPUs without this barring this one line, it would be just assigning the sum of the elements of the arrays to the result array. But this function, if we try to run it, I mean, so far nothing says our computer that we have to run it on GPU and not on CPU. How do we fix it? By using decorator from Numba CUDA. So what is a decorator? It is essentially a Python thing that means that we are wrapping one function into another function. We can, so since in Python all the objects are actual objects, so no matter what we are creating, whether it is a variable, whether it is an array, or it is a function, or it is a class, it is pretty much all the same to Python. And we can manipulate these objects in the same way, meaning we have passed the function as a parameter to another function, or we can return a function from another function, or we can assign a function to a variable, let's say temp equals some function. We can do all this, meaning that we can pass a function to some other function that will do some additional stuff on top of the function that we define. And this is a lot of function word around. But what is the syntax for this kind of thing? It is add, and maybe you haven't even seen it very often, unless you looked into the source code of some well-developed libraries. But what it is doing, we can say CUDA-JIT, which is a function meaning just in time. It is the compiler that is transforming this function that we wrote for our usual CPU execution. It is transforming it into CUDA function, into CUDA kernel. So yeah, it means that we have to pass this function into CUDA-JIT, and then it will do the transformations and will turn it into a CUDA function. So we can create this function, and now we can actually execute this function on a CUDA. So we will create the timer. Here we are defining the starting time. And here we are calling our function argvex. So we are passing blocks num, and actually thread num goes first, because this thing will return an array, essentially an array of functions. So we are identifying which element of this, not array, a dictionary. I think it will return a dictionary, but actually I have to check. I might be lying to you. But the bottom line, it will essentially create a dictionary-like structure of the functions like this that were converted to the CUDA format. So we are identifying the element of this dictionary, I think. And then we are passing the algorithm in the same way as we would do it with any ordinary function. And then we have to run this little command called synchronize, because this command is essentially telling wait until all the cores finish the execution and only then perform the next steps. And we are doing this so that our time end actually measured everything correctly. So once again, we are getting the current timestamp and we are subtracting the starting time. So let's see whether it will be able to execute. Actually, it is. We can see what about time end. It took fraction of the second. And we can see whether the results actually are working, whether we have actual results. So we were supposed, so this function is written in such a way that it's assigning the result of the summation to the C array. Or considering that we are passing the device C array, it should be this. And we are getting something strange. Instead of a proper array, we are getting something CUDA device array something. We are getting the address of this array because this array is still stored in the GPU memory. We have to copy it first to our CPU in order for CPU to be able to transfer it, to turn it into something that we can interpret. So to do this, we execute command copy to host. So you see, first we could have done copy to device. We actually done it a little bit different, but now we are copying to host to the processor. And we are copying it to the C array, which is the array that we created for storing this kind of information on our CPU. So let's see whether it does something. Yes, here we got our results, and we can actually store it as a separate variable. And yeah, now we can inspect it in a normal way. Okay. First an element. Okay, good. So these kind of things actually handles all, like we are determining all the little details. We determine the number of threads, we are configured the kernel, we manually converted this function into something that can work with CUDA, which is not always necessary. What if we do not need optimization like this? What if we do not want to think about all the thread numbers and so on? Well, we can work with a higher level library, and in fact, often we do work with higher level library, for example, with Torch. Now we are going to try the same example with Torch, but in order to do this, I will have to close this window, and I will have to actually activate a different environment, because similarly to Colab, I have a conflict of libraries. So I will shut down this kernel, and I will activate an environment when I have Torch installed, which actually works without clashing with Numba. So I am activating, first I'm deactivating this thing. And now I am activating my Torch environment. And now I'm running GPlug again. Yep. It is loading. So let's do the same stuff, only with torch. I will create a new notebook. Okay, here we are doing similar stuff, but with different libraries. First, I'm importing torch and NumPy and time our things. It is important. Okay. Let's remember, actually, let me even have a look whether I can definitely copy this thing. So, and I can create the arrays again. So we actually can do this in a couple of ways. The way it is done in the materials, let me move it to our screen, is we created the arrays directly through Torch, and we send it directly to CUDA. So the benefit is we do not have to allocate memory in our CPU. I mean, the sizes like this, it's not particularly important, but if we had a huge array, then yeah, creating it directly in CUDA would be better and would diminish the overhead because of sending the data back and forth. But in practice, something that we also often have to handle is actually the data that we do not generate from a range, but that we create, that we got from somewhere else. So for example, we are doing some kind of machine learning, and we have a huge data set of images, and we are loading them normally with some kind of image reading library, either with NumPy or with Pew or with something like that. So in this case, we could do this by implementing, by first creating the normal CPU array, and then by converting it to tensor with Torch. Actually, let's try both things. Let's do it first with creating stuff directly on Torch, just to see whether we get the same results. And invalid syntax, yes. Okay, so we have A, which is a tensor. So the type is directly Torch tensor. Here it is. But can we do the same with the original arrays that we created here? Let's see. We are creating, let's say, A to B2. And let's try converting this to the NumPy array. So Torch, does it suggest us something? It should. Nope. Okay, so I do not remember the name of the function. I thought that I will remember it from my head. Ah, because it's not to NumPy, it's from NumPy. Right. So let's see that we can convert this without issues, and let's compare the result. The type is now, once again, Torch tensor. And we would be able to do this. Yep. Whether all the elements, right, because CUDA devices and CPU. Okay, so we have still sent it to the GPU. But if we send it to GPU, or if we compare it element-wise, we will have the same results. The reason why I'm showing you this is that if you are doing any kind of machine learning stuff with Torch, you will have to deal with separate modules that are essentially data preprocessing, that are doing all those conversions of different data structures. For example, 3-channel images in RGB into Torch tensors. And in the background, it is doing essentially this. It is converting this stuff into Torch tensor format, and then you have to send it to the GPU. But so far, we have this A-B Torch things, and let's see whether we can just do the summation. With Torch, it is much easier than with NumPy. We can, once again, do the timing thing. And result doesn't start here. And we can do just summation because if those arrays are already on GPU, then Torch will know to do the operations on GPU. So A plus B, and let's once again do not forget to synchronize things. No, right? Synchronize. Good. So once again, we are waiting for all the cores to finish the calculations. And then we are calculating the time that it took us to run this on the GPU. Okay, let's see how much time does it take. So actually, it is 0.04 seconds. And with Numba, it took us how much? Come on. Yes, I don't remember how much it took us, and I cannot re-execute it because we're in a different environment where Numba does not work. But I think the value was pretty much the same. So if someone is coding along, maybe you can correct me. But I think it was pretty much the same. So in this case, any kind of manual configuration won't give us any improvement because, once again, the sizes. But a good thing is that Torch actually doesn't add a lot of overhead, so it is still pretty efficient. And let's see whether we can access our C array. Okay, A we can do. C array is actually handled better than Numba, which cannot just get stuff from the GPU. Torch is okay. It has this backend functions that manage to look at the data in the GPU, but still it is not our traditional NumPy array. So can we convert it to NumPy? Let us check. No, there is no function like this. Right. We have to do the CPU. We have to copy it to the CPU. Does it say us yes? Returns a copy of this object in CPU memory. And now we can perform the NumPy, I think. Nope. Yes, now we are having the NumPy array. So these two examples will return the same results. And as you can see, this what took us quite how many, some number of lines in Numba is actually taken in a much lesser number of coding in Torch. So in many cases, a lot of stuff in machine learning and in parallel computing can be done with high-level programming. But when you need to do when you need to implement something on CUDA is if you are developing something custom. So if, for example, you are developing if you are not just composing a machine learning model from already pre-existing layers, but developing some of your specific layers, then you might want to look at CUDA. Sometimes not. But this is about it regarding the converting your code into GPU acceptable format. We have a bit more information in this section regarding Slurm, but since we cannot execute Slurm on a personal computer, then we have to skip it. When Bura is fully functional, we encourage you to go and to try the stuff on Bura. And there will be some important edits to the script that you developed before. For example, one of the things is that you will change the partition. So essentially, the queue of jobs, if originally you used thin partition, thin CPU, I don't remember how it's called, which sent your jobs on the CPU node, then you will have, in this case, you will have to use GPU node so that it was sent to the nodes that have NVIDIA GPU cards. And yes, this would be it for the GPU part for today. If you are going to try this on your PC or on Google Colab, feel free to ping us if you encounter any issues. I do not promise that we will be able to solve them quickly because libraries are conflicting things for this kind of stuff. but we will do our best. And the next episode is actually, again, meet with resource requirements and resource management. But I suggest that first we take a 10 minutes break, considering that it was a lot of materials and we are mid our time. And right now it is 7:12 and where I am. Okay, let's do 13 minutes. Let's reconvene in half past whatever hour it is in your place, okay? 3, 2, 1, no objections. Cool. We will reconvene in 13 minutes. Okay, shall we resume?
Yeah, I think we're good to go.
Okay. Okay. Okay, so next we have some episodes on resource management. And Meet, please go on.
Yes. Just move on to the next one. So we all saw in the last episode how we can implement and add GPUs to our list of optimizing our code. And in this section, we would actually look at how we can understand what resource requirements a particular job would have. Depending on what type of science case or what type of uh, code that you're trying to run and what it performs, we can divide the jobs uh, into different subcategories for different resources which the jobs might require. So let's say if your job you're trying to classify or you're trying to um, change everything from a parent directory to subcategories based on some classification that you had for your job. Now, this would require a lot of logical processes. So you would have to go into every folder, check some particular criteria, and then you want to basically put that particular file in a particular folder in your subdirectory. These types of jobs are called CPU bound work. So usually these take up computation power, right? You cannot parallelize this type of jobs. Even if you have to go through like the entire directory, look at every single folder, and then classify it into a subfolder that you already asked the code to make. For these types of codes, usually there is no alternative just to run, but you have to run it on the CPU. One thing you can do is add a lot of memory to it so that it runs faster. We call these types of jobs as CPU bound jobs, right? In other types of examples, you would have and let's say you're trying to simulate something, or you're trying to basically add a lot of stuff in your code, like you want to perform multiplication, you want to perform convolution, you want to do some integration for your processes. These type of processes would require you to store a lot of variables. If you're storing a lot of variables, you would require a lot of memory, which is your RAM, to be high, so that all of these variables are stored in their intermediate steps and you can basically use them for your final result. These types of jobs are called as memory bound workloads. And sometimes, let's say, if you're trying to download something from somewhere, so let's say you are using a model that depends on some data set which is hosted on the internet. So if you want to like even change one parameter, or uh, try different things out for the same data set, you would have to download the source data set again and again, or make multiple copies of it. If you are making multiple copies of the data set, which is already huge, because in astronomy usually there is a source catalog that you would be working with, right? So let's say if you have like a very large data set, let's say Rubin. If you have a lot of, like, Rubin will take images of the night sky every night, right? And you want to try and find the things that are moving. So you want to find variables, things, and transient things. One way, or the way that we do it, is to basically just take videos of the night sky instead of pictures from time to time. So if you take one picture now and we take one picture tomorrow, that would not suffice, because something might have moved, which we won't be able to notice if we just take like pictures at very random times, or a long period of time. But let's say something that moves or changes its brightness in the timeline of, let's say, hours or minutes, we won't be able to detect that. If we want to detect that, what we need to do is we need to take seconds of the night sky, take pictures of the night sky every 30 seconds or 60 seconds, or let's say per minute. Uh, and then what we do is we stack these images one over the other and keep on doing that. And then we complete the stack, and then we like use the base image, and then we like subtract all the data from the other images, and then we can see that if something has changed in the images or not. If we do that, then we can also make a template that this is the base image, and then we are trying like adding all of this image, which is called a co-added image, and then from this we can subtract the initial template, which would give us the things that are moving in that particular time frame. This is called difference image analysis. I'm sure everybody of you would be already knowing this. For this, you need to keep stacking all of these images, and you need to save these images on your machine or on your HPC, or whatever you're working with. And this requires a lot of disk space. Disk space. So you need to keep saving these images, and when you're doing that, it basically becomes an input-output workload, right? And in the last case, if you're just looking at, let's say, if you have some if you want to do some classification, or if you want to do image analysis, after you have processed the image, if you want to do image analysis, what you'll do is you'll convert all the pixels of that image to a matrix, and then you are trying different operations on the matrix. If you're trying to like soften the image, or you're trying to do a black and white filter, so basically you just take the pixels and then you multiply them to some other matrix, which basically performs the function that you want on the matrix. Basically, that is exactly how computer graphics also work, as Alex pointed out in the GPU session. So like you compute computer graphics through matrices basically, and that's what GPUs are used for. So whenever you're trying to run a AI model, or you're trying to do image processing, in those cases, what you would have is basically a GPU workload, GPU accelerated workload, because you need to do those matrix multiplications hundreds or thousands amounts of time in very small sections, which is basically perfect for parallelizing with the higher amount of cores that the GPUs have. So let's look at what we have already seen earlier, but now with a clear difference. So there are three types of jobs which you would normally use on an HPC. One is a serial job, so which use the jobs which basically use a single CPU core and a single thread to run all the calculations. These are jobs that can also be ran on your local machine. If your local machine has like 16 gigs of RAM and like 4 to 8 cores, a single CPU job can easily run on that. Now, if you, as we already saw in the parallel CPU section, if you want to divide it into chunks, and if you need, that would require you to have more memory for it. If you need more memory for it, then you will categorize that as a parallel job. But for that also, there's one more classification that you would see in the notes. So parallel jobs require a lot of memory, because either you're working with OpenMP, which has a shared memory system, which we are not using because that's not supported in Python. If we are using MPI, which has distributed memory system, each process would get some amount of memory. And if you have more amount of memory for that process, the process will run faster, hence giving you a more efficient workflow. Therefore, jobs that can be run in parallel but require a lot of memory are usually appointed to SMP nodes. I'll cover that in a second, but before that, I just wanted you to know that there are these three different types. So you have serial jobs, parallel jobs, and coming to the third one, GPU jobs. That's when you are basically using an AI classifier, or you're just doing image processing, or basically something that involves matrix multiplication. Also, GPUs would still require a lot of RAM, because you need to have RAM to store all of these matrix multiplication values and like matrices, just as we saw with the tensors in CUDA. So like basically the higher order matrices you can intuitively understand as tensors, although that's not the technical definition of a tensor, but you can understand it like that. Here, so in the table, you can look at how the different job types have different Slurm partitions, and then you can use different Slurm options, as we already seen in the previous scripts. And then there are some example use cases. Now the nodes. So as you saw in yesterday's presentation by Gordon, there are different nodes available, computing nodes available on the HPC. Now, how do you select the right node for your task? So if you're just doing some MPI based, so like parallel computing or like serial computing, then the regular node or the compute thin node that we used is sufficient. But let's say your job requires a lot of resources, like a lot of memory. So like even MPI, but with like 48 cores or like 96 cores. And if you have that many cores, you require a lot of memory for the distributed system. So what you will do is you use an SMP node. SMP stands for symmetric multiprocessing. So like what happens is this basically turn the distributed memories into like a big common memory out of which the distributed memory takes part. So there's like a big pool of memory instead of like 128 GB directly being cut out into smaller pieces. This basically takes a bigger chunk of memory and then distributes it accordingly to the distributed systems, which are basically your processes, CPU cores which are running the processes. And lastly, we have the GPU node, where basically you're using CUDA, TensorFlow, PyTorch. You can ask yourself this for your job. So if you want to decide that if your job wants to, what node should you be using for your job, you can just go through this decision chart and decide if you want to do and decide if you want these resources for your job or not, and then decide which node you want to choose. All right, so I'll give you guys an example of one thing that I chose for my project. So let's say, so what I want to do is I want to basically do simulations of power spectra, which is nothing but like the correlations of 2 points in space for cosmological parameters, and I needed to do 100,000 to a billion simulations just to have like the perfect convergence of all the parameters. So you were trying to find all the possible values of this parameter depending on the other parameters, and you're trying to find out if there's a if the parameter is basically converging to some point which is basically the value of the parameter. So if you're trying to do that, let's say you would require a lot of CPU, of course, because you need to do these simulations. You need to do like them so many amounts of times. So you can basically split the simulations to different CPU cores and then sum all the results. And then for the sum result, you can then calculate if the parameter is converging or not. Does that make sense to everybody? Yep, Alex, I see that. Fatem, yeah, that makes sense. Okay. So what I'll do is for this example, I'll just go through the decision chart and I'll make my choice. So does my job require GPUs? No, I just am doing like a random selection of points based on my probability and I'm just like doing simulations. So for this simulation, for just doing a normal simulation, if you're just doing, let's say, checking at every point if this point is has a good probability given all the other parameters, then you don't need GPU nodes. So I'll not be using GPU nodes. Now, now I can think of if my job needs a very large shared memory space. It might, depending on how big my simulations are. But let's say if I'm not if I don't need a lot of, so like if there are only 4 parameters or 5 parameters that my final value is dependent on, then I won't need 128 gigs of RAM. So no. Then is your code written for distributed memory, which is MPI? Yes, my code is written for that because I need the process to be split into multiple chunks so that I can get the results faster. Then I'll use an MPI node. All right, what if it wasn't? What if I just wanted to do like 10 simulations or 100 simulations? Then I won't need an MPI job. I can then ask myself if I need OpenMP or parallel tasks, which I do not need because there are only like 100 to 1,000 simulations, and then no, and then I'll just use a regular CPU node. Does this process make sense to everybody? Are there any questions so far? All right, I don't think there are any questions. So we can move to the exercise. I just want you to basically decide based on the decision chart above where you can basically place each of this uh, tasks. So like there are five different examples, and you just need to classify. The solutions are there, but I would encourage you to basically go through this exercise and just type in chat what what node would you think that all of these five processes would use. So is it a GPU node, an SMP node, an MPI node, or like a regular node? Depends on how much RAM you need for the distinction between SMP and the regular node. But yeah, and as you will see, there can be processes which can be of mixed type. So you can either run them on GPU or on CPU, and then you need to make a call which one you want to choose. Let's do this exercise for the next 10 minutes. It's 11:16 for me right now. I'll wait till 11:26 for everybody to just come up with answers for the type of nodes for these five exercises. And if you like are confident enough in your answers, please like paste them in the chat. Uh, if you have any questions with the exercises, then also please feel free to ask.
Hi, Meet. I have a question.
Sure, go ahead.
Yeah, so in the case when we use Slurm job arrays, so each array is supposed to take like different inputs, right? So it will take different some input values and run the whole thing separately.
Yeah, so let's say I'll give you an example. So you can see the fourth exercise. So simulating and fitting microlensing light curves, where each fit is run on a separate CPU, right?
Yes.
So in this case, what you will have is let's say you have three types of microlensing events, right? Different types, and in each event you will have a few light curves that you want to simulate, like and fit, right?
Yeah.
So when you are trying to, let's say, fit all of these light curves, what the model does is that it picks up each folder of like one light curve,
Yes.
and then it runs the fit for that, and then it provides you, and like you have to modify the light curves to be in a specific format for running that basically model for
Yes.
fitting. And for each folder, what you would want to do is you want to like loop through all the like, let's say the first event is of type A, right? And the type A has A1, A2, A3, and like
Yeah.
100 light curves like that. So what you want to do is that you would like to your Slurm job to basically go through all the folders
Yeah.
for that particular. So what this array will do is that instead of just like having a folder called A, you can then put array from 1 to 99 or 1 to 999, which would then loop through your folder name, which is
Yeah.
A1 in this
Yes.
case, A999.
Okay. Okay. I think I understand. Yeah. So, so it's like when I can think of all possible permutations and combinations that I need to run, but they have no connection with each other. So I can just run them such that each CPU is taking one combination such that everything runs at the same time.
Yeah, so like think about this. If you would like to like run fits on every folder, right?
Yeah.
Now your Python code might do that. You can like make a loop that it runs all the
Yes.
codes. But then how would you like split them into chunks for your Slurm job?
Yeah.
And you will basically be running one Python job, right? At the end.
Yes. Yes.
Instead of that, what you do is you split the job, like the folders in the Slurm batch itself.
Okay. Okay. Yes.
So what you're doing is for the Slurm, you are basically allocating one job to one folder. And then what this does is that if you want to do that, then you would have to do S batch A1, S batch A2, S batch A3, right? 999 times. Instead of that, you just do S batch 1. And then in the S batch, in the Slurm file itself, will be just an array of all these 999 files.
Yeah. Yeah, so the input of different folders that I have, they can be assigned programmatically at the same time very quickly. Yeah. So I
Yes.
was thinking about, so I have run my course on PBS clusters and now I'm doing things on Slurm. So I'm new to Slurm. So I have written some code. It's not like I have not written, but I have not used these batch jobs because it was not required till now. So I had a question in mind, like, so there are some
Yeah.
embarrassingly parallel jobs where I just take some MPI, I use just MPI
Mhm.
4.5 and I, let's say, launch hundreds of, I have hundreds of processors and in the loop, I have a for loop where I have similar hundreds of things to be launched with different inputs. But, and because
Mhm.
of that, I can, in that same loop, I can assign different processes to each processor separately and everything runs parallelly because one process doesn't need to talk to
Yeah.
the other. So this is same thing
Yes.
except that I'm using batch.
Yes. So instead of doing a for loop, what you do is you do an array. You make an
Yeah,
array of
okay.
the same of all the folders.
Okay,
It's the
okay.
same thing.
Okay, got it. Thanks.
Yeah. If you like have more doubts, you can definitely connect after the workshop and you can ask further doubts if you have.
Yeah,
That's
sure.
completely fine. All right, I think we are way past the allocated time for the exercise. Like, okay, 2 minutes, but was everybody able to do the exercise? Can you give me a thumbs up if you are able to do the exercise, or at least think of what? Yeah. 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 Yep. I see 2 people giving me a thumbs up. What about everybody else? Antonio, John, were you able to do it? Naveen was able to do it as well. All right.
Do we have time
Yeah.
for questions? Like I have sort of like a not very intelligent question. And it is like in the third exercise, we're having something that is like saying that processing objects on the batches of 1,000 per job. So I remember you saying that we're using CPUs when we are having like 100 to 1,000 jobs. But I was wondering like, what is the boundary? Like if you have like more jobs, like you're running it and with a different like process, like do you have a number in mind that like where is it that like, I mean, the job is like too many jobs?
So depends on how much your HPC allows you to do. So like even if let's say you have like 39,000 or 40,000 jobs, right? You can basically, as I just explained to Navin, you can basically schedule them in an array and just start running them. It might take you a day per 10,000 job, a day for 1,000 jobs, or 2 days for 1,000 jobs. But depending on your your CPU cores, I think there would in a normal cluster there are like 128 to 256 CPU cores, and there are a lot of computing nodes as well. So if you like, let's say take 5 CPU cores and then assign 24 five computing nodes, and then assign 24 CPU cores from each node, then that would basically allow you to have like 24 into 5 amounts of number of jobs that can run simultaneously, right? Does that make sense?
Yeah, true. Right. Okay.
And then it you don't have to basically think about how many jobs can you submit. It's more about how long it would take to do these jobs, because you can submit a lot of jobs at the same time. The only thing is it will take a longer time to basically do all the jobs, go through all the jobs.
Right, true. Okay.
Even if your number of jobs exceeds the number of cores, it can just split and then like save the chunks for later processing, if you have
Right.
given it enough.
Okay, thank you very much.
Yeah. All right then. Does anybody have any follow-up questions or any more questions for this section? If there are, please feel free to ask. If not, I think we are good to go for the next section. All right. Now, let's say we understood that that we have some resource requirements for our jobs, and we on based on the decision chart in the last section, we now know that our job is a serial one, and we just want to uh, basically assign the right number of resources for it and check if we are actually allocating the required amount of resources for our job. And that can only happen if we monitor our jobs. So first we'll learn how to do basic monitoring of our jobs, taking an example which can be used in all the 3 cases. So like you can take a single example which we'll talk about, which is calculating the gravitational deflection angle. It's just an example that we would use to basically implement the same code in serial and parallel. Uh, and understand how we can basically look at the resources that we are using, how we can monitor them, and how we can optimize our resource requirements so that the other people who are using the HPC are able to access the resources that they might need for the job which we are allocating to our job, which would not be needed if we are like overusing the resources, or our job might also fail if we are just like adding like 16 gigs of RAM, but our process requires 64 gigabytes of RAM to run. So in this section, we would look at how we can take an example of a Python code, which basically calculates the gravitational deflection angle, and then write a serial monitoring job. So like we'll just run it on one CPU and one core, and then we'll check what amount of resources that code is using, and then basically optimize our code and the resource usage based on the results of the resource monitor. So for the example, we are taking the deflection angle of light. When light passes around a massive object, due to the gravity of the front object, the light from the back. So if this is your front and this is your back, the light from the back gets deflected due to the gravity of the front object. And this in the weak field limit, which is where gravity is not very strong, which means the mass of the object is lesser, we can basically approximate it to this formula, where g is the gravitational constant, m is the mass of the object, which is the lensing object. So like the thing that is in the front, c is the speed of light, special relativity people, and b is the impact parameter, which is like the closest approach of the light ray to the mass. And for our task, what we're going to do is we're going to be calculating the deflection angle over a grid of mass values as well as impact parameters. That's the only two things that we can control. The rest of the parameters in the equation are constants. So again, let's remind ourselves of how we can write a sequential Slurm script. I think we have gone through it a couple of times. J is for the job name, O is for output file. We run it on bash, so it processes everything on the terminal. E is the error file. Partition is the compute's thin one, because we're basically doing a serial job for one processor. We need one node and we need one task. So we need one core on one CPU on one computing node. That's how we are going to be using the serial job. And then we basically execute whatever program we want to. Here, in the code, we just like using NumPy to basically have the NumPy arrays for everything. We're using time to plot the start and end time of the code so that we can monitor it of how fast it runs or how slow it runs, and then compare it to other approaches such as parallel programming. We are also using matplotlib, which is a standard plotting library in Python, to visualize our final result. Here, we then basically define the constants. We then define the parameter grid. The mass grid is nothing but a linearly spaced NumPy array of from 1 to 1000, which is in solar masses. So we have defined msun to be the value here. And the impact parameter grid is nothing but another NumPy array, which is from 10⁻⁹ to 10⁻12, which is again 10,000 values. This is also 10,000 values between 1 and 1000. And then we basically also initialize the list of the result. Now we start implementing the program. So we first start timing everything. So we start when we record the time when the program starts. What you do is you do sequential computations of, you take each mass in the mass grid, and then you take each impact parameter in the impact grid, and then you calculate the gravitational deflection using the deflection formula that we had above, just using the same thing here. And then once that runs for all the 10,000 values of the solar masses and the impact parameters, we basically end when it ends, and then we calculate that time. Then we print how long it took from the end time to the start time, which basically gives us how long it took to run the code. Then we save the results in NumPy arrays, and then we load the NumPy arrays and then make a small plot, which would basically allow us to visualize how the deflection angle changes with respect to time. If you run this, you can have a look at the plot. When you run this, the CPU sequential time would be 153 seconds. So that's a couple of minutes, and your plot would also be saved in a plot subdirectory. Then we go to the next part, where you would actually want to monitor what is the CPU percentage usage and the memory of the memory required by the process that is running, right? And to do this, I would basically shift to Bura, and I would the way we do this is by using a shell file, which is basically a combination of terminal commands, which we package in a file so that we don't have to keep running them again and again, and we can like use them in the background when we are trying to monitor some jobs for job for like resource monitoring, and then we can look at that later and understand how our job performs and what parameters or like what resources we can use less or use more depending on how the job works. So I'm just gonna can you guys look at my Bura screen now?
Yes, we see it.
Is it
Yes.
yeah, okay, great. So the first thing that we'll do is we'll create a nano file, which I'll be calling resource monitor example .sh. sh is just for a shell file, so you're just creating a shell file, which is just we'll just write a bunch of terminal commands, which would allow us to basically uh, uh, monitor our CPU usage and the memory usage. So we start with first printing an out file. So that is where our log of all of the monitoring that we'll be using, will be stored. All right. So we'll create an out file, which I would name as resource usage. Right. We just want to track what resource you're using. And then if you remember from yesterday's session, this is a callback that we have environment variables in our terminal. So there are some environment variables that we can use to print values in our terminal. So here, what we're going to be doing to identify what file this is, or like what Slurm job ID this has, because you can be running the same monitoring script for different jobs, right? And then you want to basically keep a track of what job this was for. So you can basically add the environment variable for this Slurm job, and then you can name it as .log, which is a log file. Now, what we'll do is we'll create a header for the log file. So basically, we would want a consistent header that would basically allow us to like interpret every parameter that is printed later correctly. So what we'll do is we learned the echo command yesterday, which is used for printing stuff in the command line, and we'll make a header for our log file. So we just basically say what parameters are where. So the first thing is the timestamp. The second one would be the CPU percentage. The third one would be the memory, and we will measure the memory in MBs. And then we'll use this command. If you want to check what this command does, this is a redirect output override. So it creates an override file with the command output. So whatever we wrote, it will override the out file with this. So what we want to do is we want to print this in the out file as the header. So we'll just use this command, and it creates the log file and write the header line. So in this, we will write the header line like this, and then we'll assign it to the again the environment variable of the out file, so that we are assigning it to the out file. And then what we'll do is we'll create a loop. So we'll create a loop to monitor a job. This will start when we start the job, basically using Slurm sbatch. And then when we end the job, we will basically terminate this program. I'll come to that. But this loop will run till we specify it to, like, till we stop the process itself. So you can just have a normal loop. So while true, which is like always true, because true is always true, and you just ask it to do this. What you want to do is then you will basically use this PS command. Now, what is this PS command? So this PS command here is your process status. So process status will tell you what processes are you running and what is the usage of these processes. So for the process status, you will use the U flag, which is for the user, and in this case, the user will be yourself, which will be again tagged through your environment variable. So for your ID, your user variable will be whatever you are logged in as. After that, you will use the output flags or -o, and then you will for PS there are certain commands. So you will use %CPU, which will show you the CPU percentage, and RSS, which is basically your memory in kilobytes, and the com command, which is basically what command would you want to check for. And after that, what we'll use is the awk command. And the awk command is basically a text editor. So we want to format how all of these outputs would look in our log file. So for awk, what we'll do is then we'll basically assign some variables to all of the processes. So like the command, see the CPU is $1, the RSS is $2, and the command or the com is $3. So $3 is what we have kept as command here, and then we are assigning it to Python. So is equal to, and then we'll keep it as Python, and then it will only print lines where the command is Python. So as we are using a Python file to run our code, we'll only want files in the user, like the process status, all the processes that are running with the command Python, and for our user. So we'll basically, if you're just using one job to run one Python file that we described above, then it will only log the resource usage by that file. Then what we do is we print this, and then you do strf time, which is basically string formatted time, where you will have strings for the year, the month, then the date, and then the time in hours, minutes, minutes, and seconds. After that, you will close this print time. Then you will add a separator for the second row, so like second column. Then you will print the CPU percentage. Again, you will add another separator for the third row. And then what we'll do is that we'll use the memory and then divide it by 1024. As I said, RSS prints the memory in KBs. So we want to print it in megabytes. If we want to do it in gigabytes, then we'll again divide it by 1024. Since we want to do it in MBs, we're just using 1024. And then what we'll do is that we'll print all of these things to the out file. So last time we used this one arrow symbol to print the header. This time, as you can see here, now we are appending everything. This is overwriting the top of the file. This is appending everything. So it will keep the header and then it will append output to an existing file. So this stays, and then you're appending the rest of this AWK or the awk text formatting that you used using the process status command, and then you are pasting it to the out file. So you just do this, and then here you will just again use the environment variable for the out file, so you know where it is. And then what you will do is you will sleep. Sleep is another command. So what sleep does is it tells the terminal to run this command after this many seconds. So if you do sleep 5, this process will repeat, or this command will repeat itself after 5 seconds. And then you will just complete the loop, which is done. You'll write this out. You'll do resource monitor
Hi,
example.
yeah,
Yeah,
nice explanation. For the closing of command, should it be just one inverted comma, not double inverted comma?
yeah, I made a typo there. Thank you for pointing it out.
Yep.
This should be, yep. Yeah, thank you so much. You understood everything that I wrote, right? Because terminal like shell files are a bit messy to write and understand. So if there are any questions from anybody about this shell file, please feel free to ask me right now. Are there any questions regarding the shell file? If not, we can move ahead. Thank you so much, Naveen. I made a typo. Now that is fixed. All right. Now, what I can do is I can nano and go back to the session. Like, let's go back. So everybody understood what I did in the shell script. If there are any questions, you can even ping me at the end of this course. That's completely fine. Now what we'll do is we again create a sequential JavaScript in this example to basically monitor as well as run the Python file. Again, bin bash, use it on the terminal. Job name is the name of the job that you want to give. Output is the output file, the error file, the partition, the nodes. We are using one node, the time which is 10 minutes, and the memory which is 16 gigabytes. You again list all your modules for sanity checking. You load your virtual environment again for sanity. Here is the interesting part. When you want to run the shell script, what you do is you use an ampersand symbol. So this will run in the background when your Python job is running, and it will basically monitor your bash, monitor the resources till the Python file is running. Once the Python file is executed, what we'll do is we'll kill the terminal command. So we'll kill this command. Here we use %L or one %1, which is a terminal command which terminates the first background process started in the script. So we have the first background process, which is denoted by an ampersand symbol, will be killed by this command. Once you kill this, the resource monitoring would stop. Then you can print that the job completed at this time, and then you can also print where the job, like the resource usage log, is saved. Are there any questions for this Slurm job, Slurm script? Any questions? Anybody? Or what I said is completely clear to you guys? Okay, I think everybody is following grid. And then what I'll do in the interest of time is I'll just take this script, and then I can rename the script nano resource monitor example. We'll just do resource monitor slurm, and I'll just paste this here, right? And instead of using monitor resources.sh, which is the one that it should be in your downloaded file, we'll do resource monitor example, right? We'll write this out, and then we'll save it. And we'll exit. Then we'll do patch for this. and we can run this resource monitor.slurm. This was submitted. We can check if it is started running using sbatch. It is currently in pending. That's completely fine. I ran this code earlier. If you see, there are a lot of log files in my account, and I can just look at the last one that I ran. You can look at resource usage. Let's do 861210 would be fine. .log. Okay, no. This is okay. Let me go to a later one. 2155. Still not there. Let's do 61. Only that. Okay. 1261. Added one more. Yep. If you can see, it has the Python command, the memory command, and the CPU command. So if you just run this, this is what it would look like: your timestamp, your CPU percentage, and your memory. Is everybody understanding this? This is how the job would look like. And if you look at it, in it will log your CPU usage and memory percentage, like CPU percentage and memory usage every 5 seconds. So if you start it at this time and you look at it 10 seconds later, your CPU is 100% being used. So basically your job is a sequential one, as it is like you can make out that your job is a sequential one, as it is using the complete CPU, and your memory use is 1268 MB, right? So if you look at this, for sequential jobs, your CPU should use 100%. That's what we're getting. And if their CPU is lower, then it might be an input-output job, which could benefit from algorithmic optimization. So the same thing that we discussed when Angelica asked during the when we are discussing how we can optimize stuff. So if you just want to do algorithmic optimization, that can also help with input-output stuff. Memory shows you how much RAM you have running. Here you can see 1200, right? So I have a question to everybody. Did we assign the right number of memory for this job? If not, why so? And like you guys can speak up, and if you want to type, you can also type it in chat. But I'll just show you guys again. The memory is 1200 MBs, which is around 1 gig. And here we assigned for the Slurm script, we assigned 16 gigabits of memory. So are we overdoing it, or is that okay? Would anybody like to tell me?
So the 1200 MB, is it per process memory, or is the full?
It's the full memory that we are using for like everything.
Then probably we are assigning a lot than what we need.
Right?
Yeah.
So if you're assigning a lot, what can I change in this Slurm script that would make me use the correct resources for this job?
One thing is reducing the memory from 16 to something like 2 GB or 2.5 or something like that. Simple.
Yes, that's the exact thing.
Yeah.
So from this, everybody can understand that what happens is if you're assigning 16 gigs, those 16 gigs stay allocated to your job when you're running it. Even if you're only using 2 gigs, the rest of 1 gig or 2 gigs, what's happening is the rest of the 14 gigs are allocated to your job, and they cannot be used by anybody else in the cluster. This way, you are basically using a lot more than what you require for your job, and you are also using up resources that can benefit other people. So this is one way to monitor your jobs and basically look at how you want to do this. So for this, you basically want to look at how it is changing. You can use this table if you want to check. Basically, if you have a high CPU and low memory, the job is CPU bound. If you have low CPU, low memory, the job is IO bound. As we discussed, like there are different cases that can use different amount of like resources, and then through this table you can decide what your job is doing and how you would want to optimize it. For the best, I'll go through some best practices and common pitfalls for resource allocation for sequential scripts. So what you want to do is you only want to request like one core, or you only want to request memory which is proportional to the workload, which is the saw for our case. And even for you also want to use like the appropriate partitions. If you're using a GPU queue or if you're using a serial job, you don't need to run it on an SMP core, right? Does that make sense to everybody? Is everybody with me on this? Yep, I can see everybody's following. That's great. So yes, everybody's following for me. And now we can look at some common pitfalls. So yeah, Tomislav, go ahead.
Well, I just wanted to add, maybe to emphasize it more, because the people that work on the HPC usually do that. If you do this kind of job, don't take the whole node. So this is one of the how to say unwritten rules. So if you do such jobs, take one CPU for your task and not 10, 20. So it's better to allocate CPUs per task than to reserve the whole node for your job. Just to add this.
All right. That covers this section. We were going to cover HTOP, but what happened is the job monitoring side of the Slurm, which is basically called Slurm BD, if you looked at it yesterday, that is currently under maintenance on Bura because it is in vacation time. So this material is there for you to go through, but you cannot execute this currently because Bura is in under maintenance. So with that, I think we'll be moving to the last section for today. Do you guys want to take a break for 5 minutes, or just do you guys just want to go through it and like for the next time? Yeah, Naveen, go ahead.
Yeah, I have a question. So
Yeah, go ahead.
when the memory is fluctuating, like what you showed that in a table, so
Yeah, sure.
I thought that such a code would be a good written code because memory is increasing because of usage, but also going down because things which are not being used is being collected and trashed and memory is being freed. I'm thinking that. And if memory is not being freed and it is continuously increasing, then that is something a case of not nicely written code because we are not freeing memory that we don't need anymore. Is that something?
Yeah, because if your memory usage increases over time and if it doesn't stop,
Yeah.
then there's a problem. If it stops at some point, then there's no problem. But that's why you would need to look at the entire log file instead of just looking at like the first few steps.
So for example, when you write a code where, for example, you want to read a big file and there is also communication needed between processors. I have written such codes before, but I want like other opinions like what you do. So so there is a multiple processing communication job running, and there is a file which is a big file which is read, and every other processor needs that information. One thing is I can broadcast and everything, so So only one process can read and broadcast it. But sometimes I remember that multiple processes had to read that big file. Then what is kind of solution to, because then once same file is being read multiple times, then that also creates problem because it makes the whole process slow.
Yeah, that I agree. So what you're already doing is you're broadcasting it using one node, right, to the other nodes.
Yeah, sometimes that is not possible. So even, yeah. Okay.
So then, yeah, no, this is a very interesting point actually. Uh, right up where about what we are discussing. So if you want to pass the file to everything, what you can do is either you can broadcast it through one node. That's one alternative.
Yeah.
Or what you can do is you can basically add it to your Python file itself. So you're not reading it. You can basically add or add the information to the process that you're copying. So then you don't have to spend extra RAM on basically copying the process again and again, which would make it an IO bound workload. So you don't want to do an IO bound workload. What you want to do it you want to convert it into a memory bound workload.
Yeah. Yes.
So even like you have a huge amount of RAM available to you in HPCs,
Yeah.
but the disk time and like the disk usage and the disk time would not be something that you can control through an HPC. That is fixed.
Yeah, this is a good thought. Even if I have a lot of IO bound things, I can try to convert them to memory bound. That will eventually make my whole process faster.
Would run
Yeah.
much faster. Yes.
Okay.
Yes.
Yeah. Thanks.
All right. Does anybody have any further questions for this particular section? All right. If not, we can move to the next one. So let's now look at the same example for parallel CPUs, or like parallelize it using parallel CPUs. So again, we are looking at the same example where we are working with the gravitational deflection angle that is basically dependent on the mass grid and the impact parameter grid, which is like 10,000 values for each. And instead of like for every mass and for every impact parameter to calculate the gravitational deflection angle, what we are going to be doing is we are going to be dividing it into chunks. The way we do it is, if you recall the original MPI code that we did, you set up a communicator, you get the rank. So whatever, however many cores and CPUs you're using, that will give you the rank. You get the size, which is the total number of cores that you're using. Basically, you define the constants again. You define the parameter grids, which is again a NumPy array of the mass grid and the impact grid. This is where you basically, this is the crux of how you implement and like work with MPI and like parallelization. What you do is you basically divide the chunk. So like you make the chunks, you make chunks uh, from your original data set. What you do is you take the mass grid, this is 10,000, and then you divide it by the size of your total cores. So like if there are 8 cores, then 10,000 divided by 8 would be around 250, which would be your chunk size. You're dividing it into 250 chunks, like chunks of size 250, and which would be basically number of elements assigned to each rank. So like what you're doing is, instead of uh, each like one core calculating for 10,000, like 10,000 times the array, each core will calculate it for 250 elements in an array. And then you basically set the starting index. So starting index is nothing but the first chunk, and then the end index is nothing but the last chunk. And you need to do this because if, let's say, we can divide it using size, right? But what if you could not? What if you assigned 3 CPUs and like and then each of them have like a different amount of nodes which cannot be divided, right? Then the mask grid and the size cannot be, if it's like, if it has a remainder, then the last chunk or the last ending ID would have like some more additional chunk added to it, which is the remainder from the original. Did this make sense to everybody? This is the most crucial step. Like, we're dividing it into chunks, which basically will have a starting index and an ending index. Because in this case, our mask grid is perfectly dividable by our size, it will create chunks of equal amount, like equal size and equal amount. But if it's not, then we might have a remainder which we need to add to the last ID. Does this make sense? Can you give me a thumbs up if you understood what I just said? All right, I think everybody is following this. Great. So you basically divided it into chunks, and then for each mask grid, you are learning it for local. So this local is for each rank. You do start ID, end ID, and then you do a local result, which is nothing but adding all of those local IDs at the same time. You're just initializing this. You start the local time for each rank. Then in the local chunk, you do the same thing that we did for the serial case, but for each local chunk. And you just time of how long each rank takes to run this. So you do local end minus local start for each rank, and then you gather the results. Again, we gather the results using the first rank, which is what usually people do. We can use any rank here, and after we get the results, we basically use the gather operation, which basically gathers the results from all the different operations and then saves it in one chunk. And then what you do is, if our rank is 0, which is again the default rank that we use to save the results, we'll just save all of these grids. Then we load these grids again using the same rank. So we are not using any other ranks to do this. We load the data and then we make the plot. If you look at how it will run, it will give you something like this. So rank 2, rank 1, rank 3, and rank 0 ran for this much amount of time. The total MPI time is this much. The wall time is the one that took the longest, because even if you have like four people doing the same thing, the time taken for everybody to complete the thing will be the time taken by the person who takes the longest time to perform the task. Again, we would let's take a small break of 2 minutes just to understand what happened in this code. Like, just go through it once again. All of you guys have access to the materials. Just take a small break, 2 minutes, and then we'll get at how we can do resource optimization or resource monitoring for now MPI jobs. Let's see if our job ran till then. Can check if the job. Yep, the job ran. What was the ID of the job? Let's check. 861387. Did it print? Unless you can just do resource usage 861 1387. Log. Yep, it did not work. We might have missed something in the code, but if you just paste it using this, the one that we did in the last session, that should work completely fine. All right, are you guys ready for the last section of like job monitoring for parallel jobs? Should we move on? Yes. Think everybody's ready. Let's start. So, job monitoring for parallel jobs is almost as similar to what we did in the serial case, but in this case, what we do is we add a process ID. So when we use the Slurm script, I'll go to the Slurm script a little bit earlier this time so that you can understand how our job resources would be monitored and how we can improve upon that. Because in this case, the job monitor that we have won't give us a full story. This is a spoiler one. So here we again have the normal components, but here the main thing is we request 2 nodes and we request 4 tasks. So like this will again be 2 cores on 2 CPUs, but there is a caveat. When we try to monitor stuff in the parallel side, what we have to do is we have to track the process ID, which is the PID that we have here. If you look at the last, I'll just open that here for everybody to look at. If you look at this and this, the only new thing to add here is the PID. So if I just want to convert it into the one that we have for the parallel one, I'll add a PID here, which would have a process ID of whatever job we are running. And here, instead of the me having output as CPU, RSS, and COM, I'll also add a PID, which is the process ID in front of CPU. Now, since I've given process ID the first as the first environment variable here, like is the first one that you're printing in the output, this will be $1, CPU will be $2, RSS will be $3, and command will be $4. So the command here will have to change from $3 to $4 for Python, right? And here, if you can see, it's all everything else is the same. We just add $1 here and a $4 here. That's it. That's all we got to do to basically add add the resource monitoring capabilities for the parallels thing. Why we only need process ID? That I'll make that clear in a second. But if you see here, we are using 1, we are using 2, we are using 3, and we are using 4. So here, instead of doing this for 2, because RSS is $3 now, what we are printing is 1. Then we're printing $2. Then we are again separating it using this separator, and then we are finally printing $4, which is the command. So this time it will also print the Python command that we're using, right? If you look at this, this is the complete way that you can monitor your jobs for parallel jobs. And I can add this out, and yeah, and then I can exit it. And actually, if you look at the log file that I loaded earlier, it was actually for the parallel case. That is why I shifted to the section that we are looking at, and since I didn't want to spoil this. If you look at it here, you can see that there's a timestamp which in the exact format that we wanted it to be printed. Then there is a process ID. And then there's the CPU percentage usage, there's the memory, and there's the command. So we're using Python. Since we did not want to specify that we're using Python, we just like added it as a buffer. In the first one, we don't need to basically print Python for every command. So yeah, we only had the timestamp, the CPU, and the memory. In this case, if you look at the process ID, how many distinct process IDs can you see? Can anybody answer? If you look at the process IDs, how many distinct process IDs are there? Anybody still awake?
I'm trying to go through it. It looks like 2.
2, right? There is 11410 and 11411.
It seriously seems like something like n unique function is needed for this kind of estimation.
Yes, but here I'll just answer this, that there are 2 unique process IDs, right? But here, if you look at the Slurm file, we actually asked for 4 tasks. So there is an issue, right? What might that issue be? When we are trying to run this using process IDs, what happens is it basically, the process ID takes each computing node that you have asked for in the monitoring section. So 11410 is basically monitoring both of the cores on one computing node that we asked for. Similarly, 11411 is looking at the other 2 CPU cores that you asked for on the other computing node, right? And if you can see here, at some times we actually use 8 gigs of memory, right, for some processes. Therefore, when we look at it here, this time we still don't see that we cannot still basically understand what each rank is doing, because we specified 4 ranks, right? Does that make sense to everybody? If there's a question here, please ask, because this is the most crucial step for understanding why we cannot do normal job monitoring for jobs that run on multiple nodes with multiple cores. Does this make sense?
Can you repeat this last part again?
Yes. So yeah. So basically, when we use this PID command, right, we are using this process ID. There are 2 distinct process IDs here. Fatima, is
This is
fine?
true. Yeah, because you only have like 2 IDs. Yes. I
Yes.
also guessed 2. So this was correct, right?
Yeah, this was correct. But you actually asked for 4 tasks, right? There are 4 copies of the original code running on like 4 cores.
Right.
But you only asked. So what you are seeing in the process ID section is the number, the total usage of the nodes instead of for individual tasks. So like when you ask for 2 nodes, this will the Slurm script assigns you 2 computing nodes.
Right. True.
And from these 2 computing nodes, you are basically asking the Slurm script to have 4 tasks. So each computing node would give you 2 CPU cores to run your tasks on. So 2 CPU on one node, 2 CPU cores on one node, and 2 CPU cores on the second one. Does that make sense?
Yes, absolutely. Yes.
So what happens is when you try to monitor this using the shell file that we just had, we can only look at the total output of the nodes, but not the individual cores themselves.
Oh, okay. Okay, fine. Now I get it. Thank you.
Yeah, and because of that reason, we want to have a monitoring system that can basically monitor all the tasks for us, like all the ranks, right? Instead of just like the 2 cores, like the 2 computing nodes that we had, and like look at how each rank or like each core is doing instead of just looking at the computing.
Oh, okay. Okay, fine.
Right?
Yeah, fair enough. Thank you.
That we can do using psutil. psutil is a Python package which basically allows us to collect resource usage information from our script itself. So like we don't have to add a job monitoring file at all. When you do this out file, if you look at when you're like specifying the out file, you can just open like get the results in the out file itself. You don't need to have a specific monitoring script for your job. How we do this is we basically add PS utils to our import first. We use the same setup as we did in the uh, earlier parallel CPU code. The new addition here is that now we are adding monitoring. So instead of having a separate task for like a separate shell file for basically getting the process ID, we are doing it using the OS command here. And then for each process of that process ID, what we are doing is we are using the process from the PS util library. So from this process ID, we are getting the ranks or like the individual processes running on each process ID. So this is what we got as our output in the last code. We are now using that, using PS util to get each process. So like each core, how it is performing. All right, is this clear? Yep. All right, so now what we'll do is we'll define a Python function that basically monitors this. We'll have an interval of 5 seconds because that's what we kept for the shell file as well. We can keep it to any amount of time. You can also do it for 1 second, 2 seconds, but that will just overload your log file. So depending on how much you want to information you want, you can do that. Again, we have a simple loop while true is always true. So what you'll do is you get this the CPU process for each rank. You'll get the memory process for each rank, and then we'll also convert it into MB. And then you'll print rank, CPU usage, and memory usage, which is perfectly what we would want, right? And then you would like stop this loop for 5 seconds, which is what you kept as the interval. And then what you will do is you will start monitor threading, monitoring threads. So what you will do is instead of like starting and ending this at some particular point of time, you want to do it when the code is running, like over the time period the code is running. That you can do it using this threading command. So you do this threading, and then daemon is nothing. Okay, daemon is basically your background sub processes that like are always on and which you can use to monitor processes. And you are monitoring all these jobs. So like you are targeting the monitor script, and you are then starting the time. You're starting the job here, and then again you are defining the parameter grid. You are divided into chunks. You are dividing into like local results. You are timing the local results, compute time, gathering, and then you are plotting. So instead of that, now what we'll do, we use like the PS util library. Now we can have like output for each rank, and when you actually check the output, what you'll have is like this. When the first, it will just take some time for the job to start. When it starts, your CPU usage is almost 100 for all the ranks, which is very good, which means your CPU is perfectly being utilized, and your memory is less. So it goes like 200 memory to 200 to 300 max. So would anybody of you like to tell me what memory we should allocate to this Slurm script? Anybody?
Yeah, it's the total number of processes multiplied by whatever individual, slightly more than that.
Yeah, so if you have like 300 for everything, 300 MB, you would require 2 gigs of RAM max, right?
Yeah.
Therefore, we are again overusing resources, right? And therefore we need to monitor our jobs to better use resources and like keep resources free for everybody to use on a shared environment, which is your HPC. Here, there is a simple comparison between the shell script and PS util, but I already like emphasized on how PS util does the job in a more better way, because we can look at individual ranks instead of just looking at the process IDs for the computing nodes. And some like resource allocation practices, you can use n tasks, which is basically what we did. You can use CPUs for tasks if you want to do like shared memory stuff. If you want to do hybrid codes, which use MPI plus OpenMP, then you can use n tasks and CPUs for tasks simultaneously. You should also distribute across nodes carefully. So if you are basically overusing nodes, so like if you're using 2 nodes and then you're using 16 MPI ranks across 2 nodes, that's a lot of load on the 2 nodes, which you should not do. You should divide it in a proper manner. And if you're using memory, you are using memory per node and not per task. So instead use memory to request memory for the entire process instead of just using per CPU. And then you can check wall time and the scaling efficiency as we just did. Some common pitfalls, which is requesting 128 cores for a code that only scales up to 32, which you can see from the chunk size. And if you are using memory, like a lot of memory, you need to specify how much memory you require for your program. And that brings us to the end of this section. Exactly on time, which is 4 hours from when we started. So Alex, would you want to wrap this up?
Yes, thank you, Meet. That was a lot. That was very good and detailed intro, and hopefully the participants will go back and look into it into more detail, and hopefully it will help us all to be better users of the future HPC facilities on which we will be running our code. So, yeah, I will not be spending too much time on the wrap-up. Obviously, that was only an intro. More detailed knowledge will take reading a lot of documentation as well as practicing and experimenting. Keep in mind that all HPC facilities are different, so it's always a good idea to go read how they're organized and what are the rules, the behavior rules at this particular supercomputer. We think about organizing a more in-depth workshop, but this is neither here and there. We will see whether it will work in the upcoming months. And please remember that your accounts on Bura will stay active for a few more weeks. So you can still run the exercises and try those things that we didn't have time to try. Yes, Tomislav, go on.
I wanted to mention that if you would like to continue using Bura for your scientific output and inside your science collaboration, you can contact me and we can arrange your permanent account on Bura. But it should be connected with the Rubin Observatory and with the LSST, and probably with your science collaboration. So if you need resources, you can have access to Bura, and we can arrange it. Also, if you have been looking at the partitions on Bura, usually you use the compute STIN partition, but if you look more, you will see also that there is SC jobs partition. That's a special partition for array jobs, and astrophysics is mostly using this partition. So if you have also programs, and that's usual for the astrophysicists to have a parallel program with a lot of different parameters running parallel. This array was made especially for this kind of job. So if you want to run it, again, you can ask me, and we will open a permanent account, and you can use this partition too. And that's all what I wanted to say. I hope that Gordon did a nice introduction yesterday. We are also thinking to have a continuation of the how to say, not the workshop of the science collaboration, but the workshop for the use of Bura for one afternoon. That would be more like a place to meet with the Q&A, like an open session probably somewhere in October or November, so that you can come and ask whatever you wish, whatever you want. Also, we can do some sessions more advanced if you are interested, if there are more people interested in it. Yeah, so that's what I wanted to say.
Tomislav, there's a question in the chat that's asking, do only LSST members get the access? So would you like to take on that?
Yeah. Okay. So currently, Bura is in-kind contribution of the Croatian participation group at the Vera Rubin Observatory. So as an in-kind contribution, this is specially focused for the LSST member. And yeah, I mean, okay, you can ask, and we will see how this can be solved or how we can help. But at this point, we are more focused on the members of the science collaborations. Currently, let's say that we are more focused on the transient and variable star science collaboration and the Milky Way and the solar system. But of course, all other collaborations are more than welcome. But we have a good collaboration with those science collaborations. And if you are looking for the data on Bura, at the moment there are no observations, no data on Bura. In the future, we plan to transfer object catalog, so only object catalog, which is much smaller, and we are thinking to be focused more on stellar part of the object catalog. But it looks that extension to the whole object catalog is not so big, so it's highly probable that we will be able to keep the full object catalog. That's like few tens of terabytes of data. Unfortunately, we cannot provide storage for images and for anything else. But I think that with object catalog, you can do really a lot of science, good science. You have photometry, you have magnitudes, and a lot of things I think can be done.
Thank you so much.
Can I ask one quick question?
Go on.
Sure.
Yeah. So what kind of resources are available on the cluster? I think there was some slide, but I forgot. Could you please put a link for that?
You mean the partitions or the software?
Computer resources. Yeah, computer resources and
computer resources. Okay, just in short, there is a cluster node with like 6,000, 7,000, I don't know, cores, and then there is shared memory, SMP. It has much less nodes and CPUs, but the available memory is quite big. So if you need a large catalog that should be accessed simultaneously, the SMP nodes are great. And these are the two main parts. Then there is a GPU, but at the moment GPU is not working, and the focus of Bura was never a GPU cluster. So we are more focused on CPU cluster, the biggest one, and the SMP node with the shared memory. But I think that in the I will check if Gordon presentation has this info. If not, we can put the presentation about Bura for astrophysicists where all those data are available. At the moment, I don't have it anywhere online. I can send you. I mean, if you want, I can send you in the mail the presentation. Usually, is the presentation that I do at the LSST at Europe and this kind of meetings and workshops.
I also pasted the webpage of Bura in the chat if you just want to have a look at what Bura is and like what computing nodes it has.
Hey, great. Yeah, thanks a lot. Yeah, these are just the pages of the Center for Numerical Modeling and Computing at the University of Rijeka. So here you also have a short description of what Bura can offer.
Because you can just like look at this, and I think all of your questions would be answered. Like this is
Bura, okay, you find it. Yes. Yeah. So this is what I was talking about: clusters, SMP, and some GPUs. But let's say the cluster and SMP are the main part.
Okay.
Of course, we plan to upgrade it in the near future, but I cannot assure you now that this will happen, so I will not talk. We are thinking about also building a GPU cluster, but it depends on of course, on the fundings that we receive or we don't receive. So
Yes.
at the moment, this is a situation that you can find on the internet pages.
Yeah,
Thank you so much.
Really great. Yeah.
And of course, and one more thing, that if you look at the number of nodes that are running, you will see that about 30% of the nodes are running. That doesn't mean that 2/3 of Bura is broken. It's just because of the electrical power that Bura used. There is not enough demand for the whole of Bura to be running. But of course, if you have something more intensive, then we can turn on more nodes. During the summer, there is much less demand, so part of the Bura just shut down to save the energy.
Okay. Any more questions while we are still all here? If not, then thank you everyone for the attendance. You will get a link to the post-survey form to gather your feedback, and we will be very glad to hear what you're thinking. And that would be it for today. And have a nice whatever time it is where you are. See you some other time.
Thank you very much.
Yeah,
See you,
thanks,
bye.
Meet
Thank you,
and Alex, for
everyone.
today.
Thank you.
Thank you,
Bye.
Alex, for hosting us.
Thanks, everyone. Bye.
Thanks.
Thank you.
Bye-bye.